developed in order to improve the scalability of the analyzers. And then I also talk about some selective X-sensitivity techniques that we developed to improve the analysis precision in a cost-effective way. And then I'd like to talk about the synthesis part. And synthesis is very opposite notion to the analysis, but in this case, we achieved a very good performance in program synthesis by using a combination of static analysis technologies. So I'm going to talk about that one. And then in the third part, I'm going to present our recent proposal about about the framework for designing a safe modular static analysis. In this framework, we ask the designer to prove just one property. We call it advanced lemma, in addition to the usual properties that we prove when we design a correct abstract interpretations. Okay. All right. Before I continue, I'd like to mention the colleagues, my co-workers for the sparse analysis. I work with Sunggeun, Ki-hong, Min-sik, Young-bom, Ji-hun, Deok-hwan, Jae-hwang, Yoon-seok, Hee-jung, Won-chan, Woo-seok, Hak-ju, Dae-jun, and Jae-ho. And for program synthesis, I have worked with Dong-kwon, Woo-seok, Hak-ju, Yong-ho. And for the modular analysis, I work with Jun-yap. Okay. Right. So the sparse analysis thing. The story begins in about 15 or more than 15 years ago, more than say 2005 to 2007. We have developed a static analyzer for almost the full set of C programs to find a memory safety property like a buffer overrun or memory leak, double free, null dereference, that kind of bugs. And we saw that it can find some relevant bugs in real C programs, and we saw some opportunity in commercializations. And fortunately, one company approached us, and they were willing to commercialize our static analyzer. And so it was around 2010, and it was from there we worked with them to make our academic tool to be more practical and more attractive to the real software engineers in the field. And now the major product is the safety and security checkers, the bug finders, not verifiers, for more than 25 programming languages. And after we decide to commercialize this one, transfer this technology to the company, we have worked for more than 3 years with them to make it more attractive. And by that, we mean that we had to compromise lots of things. So we have to give up some, soundness and so on and so forth in order to reduce the number of false alarms at the risk of losing some real bugs and so on. But yeah, it was quite an experience for us. And after that, and these are the some from their webpage, they boast about static analysis technologies they are using when they develop their tool product. And actually, that is underlined. This one is we named the analysis engine that we have developed in our lab. We call it Sparrow. And from here to here, there are lots of compromises. Okay, so the tool become less sound, less and less sound. Okay, after we worked with the real commercial team, we came back to our lab, and we scratched our head, and we'd like to see how far we can go with original sound analysis. Okay, so it became our workbench. So we remove every compromises and come back to the original implementation with the original design. And we'd like to see how far we can go in terms of scalability first. Okay, and then we achieved this performance in 2012 and 2014. We were using our sparse analysis framework. And we achieved a scalability like we can globally analyze the C program of 1 million lines of C programs in about 10 hours on a regular notebook computers. And at that time, that was the best performance, I think. And this right graph shows the exponential improvement about the scalability. And every information is done, every code is available in this GitHub. And I'm going to talk about this framework to you, because if you are interested in building an analyzer that can scale up to some level, maybe you're interested in applying the same technique. Okay, the idea is that we have to exploit the semantic sparsity. And by semantic sparsity, we focus on two sparsity that can happen in semantics. One is a spatial sparsity, and the other one is a temporal sparsity. By spatial and temporal sparsity, I mean the memory and the flow edges. I will show you the intuition shortly. And our sparse analysis framework is that it's general, and also it's important that to be precision preserving. Given a abstract semantic function, f sharp, we apply our technique to exploit the spatial and temporal sparsity of the semantics of the input program. And we using and we sparsify the semantic function, and we compute that fixed point of that sparse function. And still, we will not guarantee that the fixed point, the precision is preserved. Okay. And actually, the reviewer says that this kind of theoretical result is very general, thanks to the because we are based on the abstract interpretation framework, based on the semantics of the program. And they say that it could be applied to many other analyses. PLDA papers have been accepted. That were simply instances of this framework. Okay, so it's very thankful review. And the spatial and temporal sparsity is this one. So the analysis that we are doing is that for each program point of the C program, we try to analyze, we try to estimate the machine state, memory image at each program point. Okay, that can happen during the executions at the program point. And usually what we do is that consider this straight line code. And for each program point, naively we can just bookkeep the whole memory image, okay, at the point. And that is the waste, because let's take a look at the orange box. And instead of bookkeeping whole memory image, we can just focus on the memory that will be accessed by that next statement. Okay, so for example, in the first statement, x equal x plus 1, it accesses only x. So we don't have to store every image there. We can just have the orange box for the x entry. And second statement is the same. Second statement only access y. So we can have only the entry for y. And for the second part, it accesses g and x. So only the two entry of the memory is necessary. And so on and so forth. So for example, for this one, suppose that A has a pointer to V, variable V, and B points to variable Z. Then for this point, instead of this whole memory map, we only need these 4 entries. That's the spatial sparsity that I mentioned. And the temporal sparsity is the yellow line, the orange line, orange arrows. So instead of following the semantics, of that is explicit in the program text, we can just follow the semantic, dependencies. So for example, after we update the X entry there, instead of passing that memory directly down to the next statement, we can just pass the post state directly to the next use point. Okay, so the orange flow is a kind of data dependency flows. By following those things, is much sparse than the flows that is explicit in the program text. So our framework is to exploit this sparsity in full, in some sense. So in the formula, what you do is that we compute the fixed point of that function. The function's input is a table of program point to the memory state, and we compute the stable table value for that fixed point value for that function. And For small f, C means that the semantic function at the program point C. And this big join operation is that from the flow in state, we join all the abstract memory input state into a single abstract memory, and then we apply the transformation function and return the post state. And the point is that where we collect from where we collect the memory is that from the definition point of the memory area that I'm going to access. So for example, the L is the memory location that will be accessed at the current program point C. And L is defined in C prime, and L will be used at C. Then we are going to bring the post state of the C prime and directly to the C point for that memory location L. Okay. So the data dependency relation is that location L is defined in C0, will be accessed in Cn, and in between L should not be defined. That's the basic idea. And please note that we are working on the approximate information about the definition and use information. So the D hat means that at C0 point, this is the set of abstract locations that can be defined at C0. And U hat means that at Cn point, it will be used, the set of memory location, abstract memory locations that can be used. And in between the point, it should not be defined in the intermittent point. Okay. And our case is that the precision, as I mentioned, our frameworks guarantees the preservation. The precision is preserved. Okay. If the following condition holds, the D hat and U hat must be an over approximation of the real thing. It must be true. And another interesting property is that second one. Actually, this means that the spurious definition point, definition locations must be included in the use case, in the set of use set. And why we need this condition for preserving the precision is the following. Suppose this 3 statement in the box, and suppose this yellow arrow is the real definition and use chain. So the X is defined here, and it will be used here. In between, X is not accessed, is not defined. So this is the real diffuse chain. In our estimation of diffuse chain, the definition is that, okay, suppose that by our analysis, this statement, we conclude that this statement can define X, may define. So from here to here, we have to draw this approximate diffuse chain, chain. Then we are missing, actually this from here to here, we cannot draw because here we conclude that X may be defined. Okay, so this is wrong. So by the second condition, what you do is that we can draw the diffuse chain from the original thing to the intermediate point. Because whenever there is a definition, we have to say that that must also be included in the use case, and then we can draw this edge. So by the second condition, we can achieve the correctness here. And actually, this can also contribute to the preservation of the precision. Okay, I will give you the intuition in the next slide why. Okay, and you may wonder, okay, this D hat and U hat is going to use when we do a sparse analysis, and D hat and U hat must be the analysis result. And what happened? What you do is that we compute the D hat and U hat by a separate pre-analysis. Okay, we can just design yet another sound, quick and very crude analysis to just estimate the D hat and U hat for each program point before the main analysis, before we start the sparse analysis. and we guarantee that this property always hold. And you may wonder, I mean, from the first side, this can be very mysterious because by the static analysis point, we don't know which one would be the spurious memory locations. This means that the spurious memory locations that can be defined at C. But in the second sort, it's easy to satisfy the second condition because by adding every definition point to the user point, then it satisfies these conditions. So, okay. And why that is preserve the precision is that, well, actually, you may know that the sparse analysis technique has been presented in the conventional data flow analysis community, the people who are doing optimizing compilations. And from time to, and their definition is, their use definition is that they are using a must information here. They draw the diffuse chain if there is no must definition in between. Okay, so in their definition, they draw from here to here and also from here to here. And suppose there's a may-diff here, okay, for the same location. May-diff, use, draw it. Diff and use, draw it. In between, this is a may definition, so we can draw it. So that's their definition. Our definition is, instead of this one, we're just using we can establish a chain of diffuse hops, okay? And intuitively, this one is, right? This one is bad for the accuracy. You have to join here. Here, we just pass around, okay? So that's the point, the intuitive explanation why our framework preserve the correctness, preserve the precision, okay? So that is the thing that we have developed as a framework. And the point is that, okay, we have to exploit the semantic sparsity for the memory portions and also the flow portions, okay? And after that, and we try to attack the right corner, precision. We'd like to improve the precision without paying too much cost, okay? And as I mentioned in the introduction, we try to exploit the sparsity. And in here case, we name it just selective flow sensitivity, selective context sensitivity. Whenever we analyze the function call, we try to turn on the context sensitivity only when that context sensitivity can contribute to the analysis result, the final result, whether that can improve the accuracy of our memory leak detection, that kind of thing, okay? How we can do it? Well, we just apply again, pre-analysis to see the effectiveness of the the context sensitivity, for example, by using a two-element domain. One is definitely yes, the other one is we don't know. And we just analyze the pre-analysis with the full context sensitivity turned on and see which one contributes to the accuracy of the final result. So, and by doing that kind of pre-analysis, we figured out that, okay, you have to turn on the context sensitivity for this call site, for this call site, and for this call site. For the rest of the call site, don't worry about the context sensitivity. Just go and do the context insensitive analysis. Okay, so we achieved a 24% of the improvement in accuracy in terms of the number of false alarms reduction by paying 28% more. If we do the blind context sensitive analysis, we have to pay, for example, 13 times more cost just to improve the same accuracy improvement. And we also worked on instead of doing a pre-analysis, we try to using a machine learning technique to generate a linear score function, and from the features of the program, text, lexical features, and also the analysis features. And we achieved a similar performance improvement. But the thing is that the design, this is the design cost and the train cost. Design cost is much less. Okay. All right. So this is the sparsity that we try to improve the precision. Okay. So, and from now, second part, I'd like to talk about the recent work that we have done to have a best program synthesis performance for generating a program that bit manipulating programs, okay, by using static analysis techniques. And program synthesis, we are focused on the inductive synthesis. Inductive synthesis is that given a language grammar and the input-output pairs as a specifications, and the goal is to generate a program that satisfies the input-output pair condition. Okay, and the generated program can be an overfit program that just satisfies the input-output pairs. But usually, we found that the program synthesis approach can generate almost very right programs. It can happen. So, for example, given this grammar, suppose the bit manipulation expression language. So the 4-bit and constant is 001, and the input is X, and there are several bit arithmetic operations and bit operations, exclusive OR and shift right, kind of thing. And suppose that we gave a input 1011 and the output must be 0011. And what would be the program? Try to find the program in this grammar. And then the system generate this program. Okay? And this program will generate the 0011 from 1011. Okay. And I will show you some synthesis result from our system. And given this bit manipulating language, same as before, some constant bit strings and the input variable X and the logical operations and arithmetic operations, and the shift right, left, and the triple arrow means the shift operations that disregard the sign bit. Okay, just brute forcefully shift right and shift left. Okay, and given a 5 to 20 input-output pairs in less than 1 second up to 35 minutes, it can generate the following programs. For the signed 8-bit string, it generates an absolute number by doing this operation. And for this, and it returns the sign of the number. And it can also generate a code for the average flow with 2-bit string, compute an average with the flow operation and the ceiling operation. Okay. And sometimes it's 64 bits. We call it de-obfuscation. Actually, the one application of the program synthesis is de-obfuscation. A very complicated program. We can just collect the input and output and feed it to the synthesizer. It generates a program that is much simpler than the given program. Okay, and it generates this one. And actually, this kind of tricky bit operations are already reported in the book they call Hacker's Delight. Yeah, and it generates this one. Actually, first 4 programs can be generated within less than 1 second, and last one was the outlier. It took 35 minutes. And as of last year, our tool is the best one in synthesizing the bit manipulation programs. Okay, and the key technology is applying the static analysis techniques. Okay, I'll talk about this one. Okay, so the synthesis key is how to prune the search space, and how we prune it is by applying static analysis techniques. Okay, and given this grammar and the input and output pair, what you do is from the beginning, the box, following the grammar, we just expand it and try to see whether any program can satisfy this problem, the input-output pair. And so The pruning is that when we expand, at some point we stop and rely on the analyzer, and ask the analyzer that, okay, given this program with a hole, is it possible to satisfy by plugging in any expression to satisfy this input-output pair? And then analyzer says no. Then we prune it. Otherwise, we keep expanding it. Okay, that's the idea. So definitely X is no, because it's not the identity function. This one, we can prune it, because we know that intuitively from the input by shift right, there's no way we can generate the 0011 from 1011. Okay, that reasoning is done by static analysis. So what you do is that, okay, given a candidate partial program X or box, given an input and output pair 1011 must generate the 0011, and we do just a simple-minded forward analysis. Okay, given we know the input 1011, box can be anything, top, 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 top. Okay, and the OR operation, we come up with 1 top 1 1, right? And 1 top 1 1 cannot be 0011. There is no way it can satisfy the output, so we prune it. Okay. And for sometimes forward analysis does not help. For the exclusive OR operation with the box, okay, and from the input 1011 box, it would be top, 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 top. Exclusive OR, the result would be top, 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 top. So it can be anything. So it can be the output. So there is nothing to do. So we keep expanding it. Okay, and then let's say, suppose we come up with this, candidate program with the hole here, and then sometimes we do the backward. Then for this part, okay, by doing a backward analysis, because the output is 0011, we can figure out that, oh, this box must return what value. In this case, from the backward analysis, we figured out that the box must be 1000, and then that means that this program must be 1000 given the input X 1011. Okay, and that constraint already shrink the search space, and then we can check again for these cases. So we can trim the this 2 subtrees, and we can focus on expanding this program, this part. Okay, and that is the pruning by static analysis. Okay, so we do a forward analysis, sometimes backward analysis to shrink the search space. And so using that kind of analysis, we can prune for the 5 programs that I showed, 57% from say 29, 8%, 26%, 39% can be trimmed. Okay, very effectively. All right. And in addition to that, we are competing with this is kind of competition. There is a competition ranking there, and in comparison with that, with the best tool at that time, we figured out that, okay, we have more time budget, so we have to improve further to increase the performance. And for that, we are using several abstract domains, and then we are using reduction operators, mutually defined information by different abstract domains. Okay, and in our case, very simple-minded bitwise domain, unsigned interval, and signed interval domain will help. So the reduced product, we know that, okay, given if we analyze the program using a bitwise domain, suppose that we come up with the top 01. For the same program, by using a different abstract domain, suppose that we come up with the 06, and we mutually refine each other. We know that, oh, this one must be, smallest number would be 1. So the 06 can be 16. And the other case is that from this size, the top, most significant bit must be 0. And we can refine each other. And we continue until it's stable. And we come up with this one refinement and this one refinement. And you can improve the analysis accuracy. And from time to time, and again, we apply this technique and we improved a little bit more. And in comparison with the competition tool, we found that, oh, we have more time budget. So we try to improve the accuracy. And what we do here is that we do a kind of refinement by full concretizations. In these applications, it is very fortunate that everything is finite. Yeah. So for example, that program for the analysis generate this result. And fine, we keep continuing. And by using backward analysis, we narrow down the range for the box case. The box case must be the value top 1. And from here, sometimes we can concretize in full. So you can improve a bit more, okay? So here the input is X is 1011. And this one can be, this one can generate 0011 or 0111. In this case, and box 0 and box 1 can be two different things. So the box would be the join of these two. That would be top 10. So from there, we improve this 1 bit from top to 0. Okay, very small improvement, but it can also help us to generate the program faster. Okay, so we built the synthesis system by using all these techniques. And it's available in the open GitHub. We named the system Simba. And the same performance table, but in the colorful way. And the first row says that the number of fastest solved problems for each domain. So our tool Simba was very quick in comparison to other tools to zero in on the solutions. Okay. If we give the 1 hour timeout, then the other tool also catch up. But still, Simba is better in finding solutions, except for benchmark cases that we allow the conditional expressions. So we were a bit weak in generating conditional bit manipulation programs. Okay, this is the story about program synthesis by using static analysis techniques that we have done. Now, I'd like to discuss with you about our recent proposal for a general modular static analysis framework. And sometimes we are interested in modular analysis. Maybe everybody is interested in modular analysis because that is happening in the compiler system, right? The compiler system can compile each file, each module separately, and then link them to generate the final A.out. And we'd like to do the same thing for the static analysis because it helps the scalability at some level or at some different levels, right? We can analyze each module in parallel, separately, up to some level, and then at the link time, you can finish the analysis, okay? And we'd like to do the same thing. And our experience is that sometimes, many years ago, we also developed this kind of modular analysis. We call it function summary based one. For each C function, we try to summarize semantic summary of that procedure, parameterized with the input context. Okay, and when the function is called, we instantiate the context and then generate the final analysis result for that function call. Okay, and at the time we don't have any guideline framework how to design the correct such function-based modular analysis. So we remember we do a lot. I mean, whenever we hit a very difficult point, difficult corner, then we just give up. Okay, and so we are always interested in having a more general and disciplined design framework, leveraging the AI framework, definitely. So actually, what we are looking for is that a way to formulate the modular semantics, such that that modular semantics must subsume the original semantics. And then modular analysis design is just an abstraction of that one. And in addition, we'd like that abstract semantic definition is obvious, is immediate to implement it from that definitions. So basically what you are looking for is the operational modular semantics, okay? To be a bit more explicit, suppose that given a two modules, E1 and E2, in a program, that funny symbol is the language construct. That means the link of these two modules. And we'd like to modular semantics and linking to satisfy this property. So the original semantics of the whole program must be the same as the modular semantics of each module separately, and then linking, okay? Then the modular analysis is just an abstraction of each component. Abstract semantics of the modules, and then abstract linking operations, such that the meaning of that one subsumes the original whole program semantics. Okay. That was our goal. And so the goal is that we have to look for what are such modular semantic formalism, and what would be the corresponding linking operations. And our requirement is that we'd like the semantic definition is more operational, because we'd like to have an immediate implementation technique from the definition of the semantics. It should be easy to implement the analyzer. And as a framework, I'd like to ask the user to prove just a small part of extra things, and all the rest thing is proven in the framework. And certainly, we'd like to align with the AI framework. And on top of the usual proof for the correctness, on top of that, we'd like to ask just a little bit more proof. Okay, that was our goal, and I think we came up with a interesting framework. We verified our framework in Coke, and the recipe is this one. We just defined the correct semantics, okay, given E program, and for the set of environment, okay, we just collect the state. And we just defined this, linking operation is that, okay, in E1, we define some name, and E2, we use that name, okay? So the program link the two modules, and the semantics would be like this. We just evaluate the E1 first. It generates a set of environment for the collecting semantics, and then pass it to the E2, okay? And so this is a understandable thing. And then the burden of the user is that you have to prove this property we call advanced lemma. Is that for a given expression and for a environment that can be decomposed into sigma and sigma 0, there's no condition for this decomposition. And then eval E with this partial environment. After that, we link it with the rest environment that must subsume the original evaluations. Then our framework proves that, okay, then it follows this property. Given these two modules that's linked in a program with this environment, we can evaluate the two modules separately with it divided, with the portion of the environment, and later we link. And then this one will subsume the original semantics, global semantics. So this is established, okay? If you prove the advanced lemma, this is true. And then everything is easy thanks to the abstract interpretation. What is the analysis? Abstraction of these two operations and then link operations. If we define it safe, then fine. Okay. So this is the our framework's recipe to the designer of the modular analysis. So one such operation semantics, we propose that, okay, we call it shadow semantics. Okay, for the shadow semantics is the semantics for the expression E with a incomplete environment. So we can still compute some semantic function, semantics of the program that has a free variable. Without knowing the value of X, we can still compute some semantics. And that is a shadow semantics. And then, okay, and we prove that this, advanced lemma. And what is shadow? Shadow is a composition of semantic operation symbols. Okay, and it can also be understood as a semantic representation of symbolic execution result. It's a symbolic execution result because for some free variables, there's no way to know the actual value. So we have to treat that as a symbol. Okay, so a kind of semantic representation of partial evaluation. Okay, or it can be semantic representation of the computations to finish at link time. Okay, and definitely can be infinite object. If the program has an infinite computation, sure. And if the program has an input variable that we don't know, free variable we don't know, if we figure out, if we're reasoning about the things about the free variable, then the value, possible value for the free variable X can be infinitely many, then this representation can be infinite. Okay, I'll show you the example. For X plus 1 plus 2, X is a free variable. With the unknown environment, we just say that shadow semantics would be the unknown initial environment. We read variable X, we don't know, just a functional symbol, and plus 3. That is the shadow semantics. How about the function call? It's the same. Unknown environment, we have to read F. Unknown environment, from the unknown environment, we have to read X, and we have to call because the call is there, and the result must be plus 3. This is the shadow semantics. For this recursive function sum is that given a function and the constant, the natural number, we just apply f0, f1 up to fn and summation. Okay. And this module G is free variable. And what is the shadow semantics? That would be, we just run this program with the shadow for the G. So it will be called, G is a macro, it's just a read from unknown environment, entry G, okay? So the G, call G with 0, call G with 1, call G with 2, call G with 3, and all summation. That is the shadow semantics for that, module. How about the M is also how about this one is also free variable? We don't know how many times the recursive call to sum it will be done. So we have to collect all possible cases. So this case is when the M is 0. This case is when M is 1. This case is when M is 2. This case is when M is 3, and so on and so forth. This is the infinite set. Okay? This is the shadow semantics. So using this basic idea, we give for a model language that is a call by value lambda calculus plus module construct, and we allow the first class modules, like modules can be a value. Okay, so this model language can support the functors in OCaml or generic package in Java, or template in C++. And so usual program higher order programming language case lambda calculus, and the other last 3 construct is for the module generation and the use. Okay, so this is the definition followed by another definition. They can use X or some value. And this is the model used. For example, this is the module that defines x and y, and it's linked with this part. And this part is free variable x, and that will be this one. Okay, and we can name the this module as m, and we can link it with this expression. This one is the m dot x. Okay, yeah. So this small language is a very minimal, but it has all the advanced features in module programming. So we define the semantics as usual for the functions, and also this language has the environment as a value. Okay, and the environment would be empty environment or the list of bindings. Okay. So what you do is that we can define the semantics fairly easily, and we are using a structural operational semantics. Okay. And we have to extend the semantics to do the, generate the shadow semantic definitions, even for the program that has a free variable. Okay. So the extension is easy for the structural operational semantics. We just add the, inference, more extra inference rules that can do some computations for the shadow semantics. Okay. So the dagger is the shadows, the environment that can contain some shadows. Okay, the value can contain some shadows. Okay, so the shadowed environment would be the same as before, and we can have a shadow. And the value, usual value, but it can be a shadowed environment. Okay, and shadow has a value, and shadow in our case is a read or call or the initial unknown environment. These are the semantic operations representation for free variables. Okay, so we define the linking operations from the environment given a shadow. What would be the value? Okay. We can by the linking operations we can generate the final value, or we can generate the less shadowy values. Okay. And all definitions are very straightforward. There's no nonsense there. Okay, and sometimes we have to, not sometimes we have to define the environment link with the environment, because this case is when we link the value, closure value that has the environment part. So we have to link it. We have to link, and for the value too. Okay, so there's nothing to surprise. And we define the collecting semantics, is straightforward definition. And then we were able to prove the advanced lemma that the framework requires. And then this follows. And this enables our separate modular analysis. Each module is analyzed with a different environment. That may not satisfy, they may not have a bindings for some free variables. Okay, and then the linking take care of all those unresolved computations later. And the sound modular analysis is just an abstraction, sound abstraction of those corresponding operations and semantic functions. So the function summary based approach in our case is a very straightforward application of our framework. For the closure, the summary is the shadow abstract semantics. Okay, and the call is just the linking. Okay, with this call with the the binding actual the binding with the current call environment, and then linking. Okay, so the very interesting things. Okay, so this is the thing that we recently come up with as a framework for designing correct modular static analysis. Okay, so To summing up, for sparse analysis, we have to, if you are interested in building a scalable sum and global analyzer, you'd better exploit the sparsity in memory and the control flow and the data flow, okay? And both by sound pre-analysis and right definition for diffuse chain, you can preserve the precision. For program synthesis, by using techniques that our community have developed, we can have a very good performance in program synthesis. And for modular analysis, by proving the advanced lemma for your definition of the semantics, you can come up with the modular analysis in safe way. Okay, so this is the you look very nervous that okay, thank you very much. Just yeah.
Other questions? But you have to do something when this
Oh yeah, sure.
So what do you do?
Maybe. No, this work? Does this work?
Yeah.
Okay. Yeah, I mean the mutual dependence. What you want is that okay to the programmer you have to program in a correct way. The mutually dependent modules are wrong programming skill. And if there is a mutual dependence, yeah, maybe some fixed point involved. Yeah. Yes.
Yeah, so for the slide where you're generating a program for the input and output of the F, and you're doing the for the pruning the slide. So it's still I think you just passed it.
This one.
A little bit later when you're doing like the F.
Oh, this one, this definition.
No, later on when you're doing the pruning.
Okay.
So when you're generating the tree and you're pruning, it's still going to be like exponential space, right?
Oh yeah, sure.
So if there's a way you can like reduce that to polynomial time,
no,
could you?
We don't.
No way.
No, we don't dare to reduce it to polynomial space. No, we just keep pruning and see what happens.
Okay.
Yeah.
Thank you.
Okay.
Yeah, so thank you very much for the talk. I also have a question for the synthesis part. So you showed us some very cool example of hacker delight kind of things.
Yeah, this one.
With where the input and outputs were like sequences of bits.
Yeah.
And I wondered if this approach can also be used with functions that are defined like on real numbers or floats.
For the functions
when you have functions from the reals to the reals, or like from floats to floats, can you also use this kind of techniques?
I think so. Why not? Yeah.
Okay. Has it been tried?
No.
Okay.
The next one that we are currently trying is to generate the string manipulation code. Yeah, not for the floating point numbers or real numbers.
Thank you.
Okay, but I don't think any obstacles that apply the same technique for overflow. What do you mean overflow? Average or the plus? There is a semantic definitions in the competition for this language, and we just follow the semantics. Yeah, and I don't know how they handle the overflow. Yeah, and for this kind of operations, if x is minus, then y is the semantics, and that's also defined in the language. Yeah.
Okay. Well, let's speak again.
Okay, thank you.
Next speaker is Marco Milanese, joint work with Antoine Minet. Sorry? Under-approximating. Yeah, sure, thank you. Memory abstractions.
How do I connect it? Can I move? Yes. Yeah, maybe it's best. Okay, thank you. So hello everyone, my name is Marco Milanese, I'm a PhD student at Sorbonne University, and today I would like to discuss some work about under-approximating memory abstractions that I did in collaboration with my supervisor, Professor Antoine Minet. So this is the outline of my presentation. I would like to start with the introduction of the problem, then some previous works. Then I would like to discuss my contribution, so these under-approximating memory domains, and finally discuss a bit about implementation and some experiments we did. So as we know, static analysis by abstract interpretation has this very nice property of being sound, which means that the abstract interpretation of some program S will always over-approximate the set of behaviors of that program. This means that if you have a specification that here I depicted in red, which is larger than your abstract interpretation, meaning that the abstract interpretation can imply it, you can prove that your program is actually correct. You may also have the situation where your program is incorrect, it doesn't satisfy your specification, and the analysis will raise some alarms that in this case are called true alarms. There is this last situation where the program is actually correct because it's fully contained inside your specification, but your abstract interpretation is not precise enough, and thus it can't prove that the program is correct. So this situation is typically called false alarms. So in general, at the end of a sound analysis, you can have a set of alarms, and some of them may be false and some others may be true. And you, of course, want to find out which ones are false and true. So an approach to do so will be to try generating counterexamples for those alarms. And this can be done with several techniques and just listing a few of them, like model checking, symbolic execution, correctness logic, and so on. And often these techniques are constrained by some scalability issues. In particular, they have these two challenges, For example, they may handle loops by unrolling them. This is the case, for example, with the basic symbolic execution frameworks. Or also you may have a path explosion issue. And we argue that abstract interpretation can address best these two issues because for example, you have widening operators for computing the loop invariants, and so you're not forced to look for bugs up to until a certain depth of your loop. So to summarize, this is the goal of our analysis. We would like to find out conditions that trigger some bug in C-like programs. And also we want to be independent from non-determinism, meaning that the condition we find, we want them to trigger always the bug, no matter the non-deterministic behavior of your program. So for example, if you have a very simple task like this, where you have an input between 0 and 10, and you have this assertion that asserts that I must be smaller or equal than some non-deterministic value between 5 and 8. So this program is, of course, incorrect, and a sound analysis will raise an alarm here. And then you want to find some conditions that witness this bug. So in particular, we look for sufficient preconditions. So a set of inputs that trigger the bug in all cases, so in all program behaviors. So in this case, you can find that the input must be between 9 and 10. So now I would like to recall some previous work about how you can perform this backward analysis, so this analysis in
with a numeric with numeric programs. So we start with a very classical forward collective semantics. So you have a program S, and you have a precondition, which is a set of states, and you generate a new postcondition, which is again a set of states. And the backward sufficient precondition analysis we compute is defined as here. So you collect all the states sigma in your such that starting from that state sigma, you get a new postcondition, and that postcondition must be contained within S, which is the postcondition of your program for which you want to find a precondition. So we assume a simple while language which contains basic statements such as assignments, filters, and then inductive statements such as concatenation, if then else, and while loops. And it was shown in these previous works that you can compute the backward analysis inductively on the structure of your program, and this is the formula. These are the formulas for your atomic statements. So in the assignment case, you collect all the environments where, when you evaluate the right-hand side, you have some values that, when you perform the substitution, you end up in S. And for the Boolean filtering, you collect all the state of your condition, and you join all the environments that make the guard of your filter false. For the inductive statements, we can reuse the backward analysis of the subcomponents. So, for example, for the concatenation, we just swap the we first perform the backward analysis of the second statement, then the first. If then else, we do first the two then and else branches, and then we do the guards, and the two results are met together. So this is a difference between the normal analysis, the forward analysis, where you join. Here instead you have meet. And for while loops, you have a greatest fixed point instead of least fixed point, and you do first the guard and then the loop. Okay, so up to this point, we discussed only about concrete semantics. When you want to move to an abstract semantics, you introduce abstract domains. And there is a problem here because normally domains perform over-approximations, for example, in join, in widen operations as well. And these operations are not sound for sufficient precondition analysis. We want to find under-approximations instead. So the approach we used here is to reuse conventional abstract domains. So we maintain the usual shapes, but we provide new transfer functions that are under-approximating, and also a new set of lattice operators such as under-approximating join, a dual widening as well, and so on. And so this is particularly tricky because you no longer have abstraction function that can guide you in the design of these operators. So you need to use some heuristics or in order to decide which is the output of your operators. We demonstrated this approach in some previous work for numeric domains. And for example, we showed how to perform this operation in the polyhedra domain. Okay, but all of this work was done only for numeric programs. And now we want to move on with the programs such as that can also deal with memory, like in C. And so let's now see what kind of problems we need to address. So in the first problem is that you can access in C the same variable with different views. For example, you can access it as an int, but you can also access the first byte of it. And so you need a way to represent this. You can have also pointer variables, and so you need to have an abstraction of pointers as well. And finally, you can have dynamic memory allocations, so malloc, free, and so on. And you need also to abstract these. So to start from the first problem, we consider the cell model of memory, where basically you assume that the memory is segmented among several different bases, and each base corresponds to some variable. And so we assume that all these blocks corresponding to each variable are disjoint. And later we'll add also blocks for dynamic memory allocations. So you can view a memory access at byte level here using a pair where the first element of the pair is the block you want to access, and the second element is an offset of that block. This view is quite low level, and it's very inefficient because, for example, if you want to access an integer, you will need to decompose this access into some a sequence of byte level access, and then perform these access as the numeric level domain. And then if you want to read it, you need to read all these bytes and recompose that into a value. So this is very costly. So what this domain proposes to use instead a cell-based approach, where you have a cell which is a triple made of a base, an offset, and also a type. And this is basically giving a view of some specific memory location with some specific type. And the semantics, when you have overlapping cell, is that you take the intersection between the values in the two cells. So, for example, in this case here, we have a memory block, and we view it as an integer from 0 to the third byte, or also as a short. And we take the intersection between the two as the byte level semantics of this case. And cells are created and destroyed on demand during the analysis based on what you need to do. Then we have an abstraction for pointers, and we use a very simple points to abstraction, where for each pointer variable, you keep track of the set of targets of that pointer. So for example, here in this program, we have a pointer which may be initialized with the value, with the address of X or Y, depending on some non-determinism. And so at the end of the analysis of this program, we store that P can point either to the address of X or address of Y. And whenever you want to dereference that pointer, we perform a resolution of the address of this dereference, which in this case replaces the star P with the X or Y. And so if you have this assignment, you perform the assignment in the two cases, and then you join the result. Finally, we have abstraction for memory allocations. So the problem with dynamic memory allocations is that they require summarization. So for example, here, if this malloc is called several times, you can't make every time a new block, because you may also have an infinite number of blocks if you're in an infinite loop. So in general, you need to have a way to smash those blocks together at a certain point, or to have some symbolic representation of some kind. So we use a very simple domain, which is the, sorry. So first of all, if you simply naively represent this memory location as a summary block, which is accessed using weak accesses, you will find out that the result will be very imprecise. For example, here, after the malloc, the block is uninitialized, so it's at top. If you try to set it with 0, you can't, because you will be accessing it with a weak access, and so you're just joining 0 with top, and so you remain at top. So we use a simple refinement of this abstraction, where you single out the most recent block that is returned by malloc into a strong block, and you keep all the previous allocations into a summary block that is accessed with the weak accesses. So in this case, if malloc is called for the first time here, you get a recent block, which is uninitialized, and as soon as you try to initialize it with 0, you actually do manage, because this is a strong access. Okay, now all up to this point we saw some previous works, and now I want to present you how we can reuse these memory abstractions in a under-approximating backward analysis of C, basically. So our first problem we face when we want to work with a program like that is that in the forward analysis of this program, in particular of the assignment in the second line, what you do is you first try to figure out what is the location you access on the left-hand side of your assignment, and then you actually carry out your assignment. But here you can't do that in the backward analysis, because you don't know in advance, because you will need to do first the assignment and then find out which is the location of your assignment. And there is the problem that your assignment may have changed the pointers involved in the resolution itself of this left-hand side. So in this case, if you have this post condition, that is that the array of 0 is 1 and array of 1 is 0. And if you resolve the left-hand side in your backward analysis with the value, with the array of 0 equal to 1, you will be accessing the second location of your array, not the first one, and so this will be incorrect. So the intuition for our approach for solving this issue, this problem, is that we try the assignment in both locations, and then we collect together the results with a sort of if-then-else block. So basically what we do is something like this, where we try the assignment in both cases. So both is array of 0 is 0 and 1. And then we merge the two paths in an if-then-else block. So I'll show you the computation. So this is for the analysis. We start with the array of 0 and 1 equal to 0. And we get array of 0 is equal to 1 and array of 1 is equal to 0. So if you do the backward analysis of this, we use the rules that we have seen before. So the union becomes a join here, a meet. And you do first the backward analysis for the two assignments. So in this case, this one becomes bottom because you will be assigning the value 1, but at the location 1, but that is 0, so you don't have any precondition that satisfies this assignment. In the second case, instead, you get top, and so for the location 1, and so for the location 0, sorry, and so you remain with the second part of your postcondition S, which is array of 1 is equal to 0. And then in this line, you do the analysis of the two guards that will join these to the postcondition all the states that don't satisfy the guard. So in the first part, we have that you add the array of 0 is different from 0. And the second part, you add that array of 0 is different from 1. And from that, you can conclude that doing the meet, array of 0 is different from 0. So in this case, is equal to 0. And array of 1 is equal also to 0. And so this is how we compute our precondition. So to summarize this approach, whenever you have a statement S in which you have some dereference of a pointer P, we translate this into this computation here, where you replace P, the dereference of P with some target, P1 in this case, in the first case, all the way to Pn, and every time you try different possible targets, and then you do the intersection among all these possibilities. In general, since you don't know which can be the targets of pointer accesses, so you may have to put one case for every possible pointer location, but that will be very, very expensive, but still sound. But to make this practical, we carry out a pre-analysis of our program where we find out possible targets for each pointer. And this way we can rule out some candidates in our computation. So for example, here I showed that we can delete some computation. And so we remain only with the possible targets. And the pre-analysis doesn't need to be under-approximating, can be a normal forward over-approximating analysis. Adding more cases is still sound because you're performing an intersection, so you'll be making the result, even you're shrinking the result, basically. Okay, now that we know how to replace pointer dereference statements, we can carry out assignments or filters and so on. And so we can do this at the cell level domain. Okay, so the cell domain has this operation, which is the addition, where you add new cells, which is exact, so we don't need to do anything for that. It's already sound for under approximations. But instead, the cell removal, which is used, for example, in assignments, is not sound. Is not under approximating. It's in general over approximating, because what we do usually is that when we simply drop the cell, and that's sound because of the intersecting semantic. But in our analysis, we can't do this. It will be unsound. So we need to have a way to remove cells that is under approximating. So let's consider this example here, where you are doing an assignment to C1, let's say, but you still have to overlapping cell to C1. You may have C2 and C3. So our idea is that before doing the assignment on C1, we want to have a way to remove those two cells. And again, we can't simply drop them. We need to transfer the information containing those two cells into C1 first, and then we can safely remove them. So in order to do this information transfer, we showed in the paper that it's enough to perform a backward analysis of the assignment to C1 of some expression which initializes C1 from C2 and then from C3, or the other way around. And I would like to remark that this is, for people familiar with the cell domain, this is the phi function, and any over approximation on the right-hand side will be still sound here. Finally, we can conclude with the abstraction of, so with backward analysis of heap allocations. So the for semantics of the malloc is this. So we have two cases. If you already have if you don't have a summary block, what you do is you simply rename your current recent block into a summary block, and you return a new fresh recent block. If you already have a summary block, what you do is that you need to fold your current recent block into your summary block and return a new fresh recent block. In the backward analysis, it's very simple. We simply invert those two operations. So let's say that we don't have a summary block in the post condition. So this is coming from only from one possibility in the precondition, that is when you didn't have neither the recent nor the summary block, and so we simply remove the recent block in this case. Instead, if you have a summary block in your post condition, you simply revert the fold operation, and the backward analysis of fold operation is just an expand. The implementation of free is very simple. Is very uses the same ideas, so I won't discuss this in the presentation, but you can find that in the paper. As for implementation, we implemented these domains with a simple proof of concept implementation in the MOPSA platform. In particular, we focused on analysis of C code, and with these memory abstractions, we can analyze quite big subset of C. We, for example, don't support memory recursion and floating point numbers, but we support all the pointed references and casting and so on. We use these domains. So for the numeric part, we have intervals. For memory, we have these three domains that we have just seen. We have an abstraction of inputs in the form of a time invariant stream of values. So every time you have a stream, an input function, you just replace that with some variable. And finally, I added also a simple abstraction for constant strings, which is quite useful in some test cases. We experimented this implementation using the Juliet test suite. In particular, and this is a very big benchmark set from NIST. And we considered 12 CWEs from this set, which contains already incorrect tasks, and in particular, tasks where you have runtime errors caused by undefined behavior. So this is the result of our analysis. So here I listed all the CWEs, and on the last column we can see that we have some unsupported tasks, and those are mainly because of floating point numbers. We have two columns for success and imprecise. Success means that the analyzer managed to find some non-empty preconditions, so you found some state that will trigger the bug. And imprecise means that we found bottom, so we don't find any precondition for raising the bug. I want to remark that we have some good results on the categories related to some to integer programs, so integer overflow, underflow, division by zero, and double free as well. And we struggle a bit more on programs relating big buffer of memory, such as stack or heap-based overflows and so on. The problem with that is that we have a quite low-level representation of memory, and if you need to compute symbolic operations such as copies of strings or buffers or computing length of strings, you are quite imprecise in these loops. So in conclusion, in this talk, we discussed and we saw how we can reuse up sufficient precondition analysis for finding bugs in C programs. I presented some 3 abstractions of memory that are useful for dealing with the C model of memory. So the cell domain for abstracting overlapping accesses to the same blocks, the points to domain, which is used to track the values of pointers, and finally the heap recency abstraction for handling dynamic memory allocations. And finally, we saw some experimental results of this implementation. So thank you for your attention.
So if I understood well, the under-approximation for the arrays was only for a finite array, or I wonder if you have considering under-approximation for infinite arrays, or finite arrays without a non-bound.
Yes. So the problem with this. So yeah, thank you. So the problem with this is that also in the forward analysis, so there is a limitation inside our abstract domain for memory, where we basically represent arrays by having concrete values for its position of your array. So already in the forward analysis, we can be very imprecise in these kind of cases. That's also the source of imprecision in our experimental results. So yeah, I mean, in principle, you could do it, but I think it will be very, very imprecise with this domain.
talking, I keep talking. Test, test, test. Testing, testing, testing.
of SAS'24 about the types, control flow, and trace partitioning. Okay. So we cannot move with the microphone? Okay. We have 3 talks in the session. The first one will be given by Ian Smith. The title is Bin Sub, the simple essence of polymorphic type inference for machine code. So, please.
Thank you. Yeah, so like I said, I'm Ian Smith, Senior Security Engineer at Trail of Bits, and we're going to be talking about binary type inference for machine code. So I just wanted to introduce the problem space for those who aren't super focused on binary analysis. I'm not sure how well this slide is coming out in the back, but this is an example of an implementation of a hash map decompiled in Ghidra without any type inference. And so as you can see, like sort of here and elsewhere, there's a bunch of void pointers, and we're returning like a double void pointer, and it's all raw pointer arithmetic. And what we're looking to get to is something like this, where we actually have the linked list node structure type, we have field accesses, and we've retyped the array of sort of linked list heads into an array. So there's a lot of use cases. The one that I just highlighted was decompilation readability, but there's other sort of use cases like vulnerability discovery, where if you're concerned about the fields of a structure, for instance, for field sensitivity, you'll obviously need to recover those fields before you actually do your analysis. The obvious difficulty is that compilation is lossy, and this really affects all binary analysis. Types don't really exist in the way that we're talking about at the binary level. Things are thrown out. And so these difficulties have led to sort of a collection of solutions that have led to pretty sophisticated and complex type inference algorithms and type systems. So I'm just going to run through the prior work, what problems they identified, and what the solutions were, and then we're going to try to simplify those into a simpler and efficient type system. So this is one problem, which is that we need subtyping. And this is sort of an extreme example of why you might need subtyping. And what we're identifying here is sort of value reuse and slot reuse in sort of a single example. We're compiling a function called f of null and 0. And since EAX can be zeroed and then used as both parameters for the function, if you take sort of a unification, sort of reflexive relation and just do unification on the types, you're going to end up unifying void pointer and int, and obviously that becomes unclear. It's basically a type error. So we want to introduce subtyping, and so that'll remove the reflexive relation, and then we just have directional subtyping of EAX of pointer 1, pointer 2, and then we don't end up unifying void pointer and int. But once we've introduced this, we've introduced a problem for ourselves because we now have unsoundness with respect to mutability because we've introduced subtyping into a mutable language. And as you know from like ML, one solution would be to make these references invariant. But that would be kind of catastrophic for our binary type inference algorithm because then we can't relate pointers at all and we've basically failed. So we have to pick something to do. And the original work picked covariant parameters for pointers, and that's obviously not correct. If we look at sort of the rule up top, if you go ahead and store into the supertype in that case, then we're going to lose any information about the load from the subtype because we're treating these parameters as covariant, and you run into a similar problem with contravariant types. And so the identified solution is we need to go ahead and split the type parameters into 2 parameters, load and store parameter, and that's the rule from ret type D, a paper we're going to be talking about a lot, which is sort of the previous state of the art in binary type inference that achieves all of these features. And what you're doing here is you're saying that if we store into a pointer, it needs to be a subtype of whatever we load from that pointer. And so how do we actually achieve this in a type system? The way ret type D does it is you have sort of this capability system where labels are attached to type variables, and then they have a covariant and a contravariant rule between labels. And then you also have to have a transitivity rule. And then all of these rules are represented in a weighted pushdown automata. And then you saturate that automata to produce a transducer that recognizes legal derivations of the stack. And then you just explore all of the paths in that transducer to simplify your constraint set and solve for types. This leads to a pretty complicated algorithm. It's O of n cubed. It's pretty expensive. And so the idea is how can we do a similar thing, but in a simpler way. And that way is going to be algebraic subtyping. Just like off the bat, if you look at algebraic subtyping, just like you take the features that they talk about that it supports, you've got parametric polymorphism, subtyping, principal type inference, and recursive types, which pretty much knocks out the list of features that we're going to need for binary type inference. And so now I'm going to sort of just give a high-level sketch of what algebraic subtyping is, and it's roughly a Hindley-Milner-based type system. But what we're going to do is sort of bolt-on subtyping by, obviously you need a subtyping lattice of some sort, but we're going to require that it be distributive, and the way that we make it distributive is by inserting union and intersection types into types, and we'll see an example of this. And so that means that there's going to be a non-trivial type for any join or meet. And then we're going to separate types into input and output positions. They're also called negative and positive positions. And we're going to produce substitutions as you would in typical Hindley-Milner, but we're going to do different substitutions for input and output positions. That is, for input positions, we're going to substitute the upper bounds of a type, and for output positions, we're going to substitute the lower bounds of a type. And you can sort of squint at this and think about why this would be sound, right? If you have an input, the upper bound of the type is going to be all of the type capabilities that we need to use that input, and then the output is the least type that we are going to get from that output. So when we link an input to an output, we're going to soundly have a safe type assigned. So that's been pretty much at a high level. We're going to be applying algebraic subtyping to the binary type inference problem to achieve these features that we want in an algorithm. And so this is an overview just operationally of how things are going to go. We're going to have an intermediate representation that we're going to generate type constraints from. We're going to then perform biunification, which is that asymmetric substitution algorithm that I described earlier. We're going to lift it to a type automata representation to do simplifications, lower it to a C type, and then you can achieve polymorphism fairly simply by cloning call sites and then taking the join of all call sites to get a lower bound on that type. So this is just going to be a run-through example program. It's really simple linked list traversal. We're just incrementing every value in the linked list. And then the only funky thing that we're doing here is we're copying the current pointer when we're using it. And so there is the case where after the function has run, we never copied into copy, and so copy hasn't ever seen that sort of typing relation. And so this is an example of the intermediate representation. And the main things I wanted to point out here is that we are operating on sort of an untyped intermediate representation that's already recovered stack variables. If you don't do this, then you can't track subtyping relationships between loads and stores of stack variables. And you would have to treat the stack variables as sort of an abstract record, or treat the stack as an abstract record. And I'll just note that when we look at line 4 here, we're loading from a displacement 4 a value of size 4, so that indicates to us that that linked list pointer is at the displacement 4 and is of size 4. So here's the actual type syntax that we're working with. It's kind of close to what you would expect from an ML type system. The sort of difference that I mentioned is for records. We are flexible in sort of the labels in that it's pairs of natural numbers where the first natural number is the offset into the record, and then the second natural number is the size of that type. And we do a similar thing for function types where each function type is labeled by a natural number. So each of these is partial functions from natural numbers to types. And then for the pointer type, the first parameter is the store parameter, and the second parameter is the load parameter to do that sort of splitting that I mentioned earlier. And then we have union, intersection types, recursive types, and an atomic type lattice. You can use any atomic type lattice here. We use the base atomic type lattice of Anger in this work. And then, like I mentioned, we're going to actually have to partition these types into two sets, or two syntaxes. The output positions, which are those first also positive positions, and input positions, which are the negatives. And it's fairly intuitive how this works. So if you have a record type, that's going to maintain, and it's in an output position, that's going to maintain the output position syntax for the type for each of the fields. Inputs are going to flip that so that it's an input type, and then the store parameter of a pointer is going to be an input. And the important bit here is that we're going to restrict the syntax of output types to only have union types in that spot. So then we're aggregating a bunch of lower bounds on the type. And then if we look at the input type, the only real difference is that we flip everything, and we're going to only allow intersection types in input positions. So now that we have our type syntax, we can look at what constraints actually would end up looking like. So if we have a stack slot 2, for each just basic assignment, it's going to be a basic subtyping relationship. But what I wanted to highlight was this load from stack slot 2, just to look at what a load looks like. Since we know that stack slot 2 is being loaded from, we know it must be a subtype of pointer. And since we loaded something of size 4 at offset 4, we are going to introduce a record type there and point it to a free variable. And we don't know anything about what can be stored in the pointer. And then the main thing that I wanted to point out is that we have to maintain this side condition that the store variable is the subtype of the load variable. So we have to maintain that rule there. Once you have type constraints, then we want to solve for a given variable. The way you do this is by that bi-unification algorithm that I mentioned earlier, where you just substitute for variables either the lower bounds or upper bounds, depending on the position that you're in, either an input or output position. The original work did this fairly directly, so you actually perform the substitutions. But to make that efficient, you have to do it over automata. So we took some follow-on works approach, which actually decomposes this into two sort of sub-problems. One is aggregating the constraints implied by rules onto variables. So you just want to follow your constructors and then bring down your constraints to constraints on variables and aggregate its lower and upper bounds. And then since you've done that already, you can fairly easily coalesce a single type into a representative by whenever you reach a variable performing the correct substitution. So this is what decomposing ends up looking like. So when you have a constructor, you just apply your typing rules to figure out which variables are in a subtyping relationship. So I've highlighted the pointer constructor here. So at the top, you have the contravariant constraint on the store parameter. So you flip the order and then go ahead and constrain those. And so the interesting case is when you hit a variable. If you hit a variable and the variable is in the lower bound, then you need to introduce the type to its upper bounds. But at that point, you may have lower bounds on that type, which are you no longer have a consistent constraint set because they might not be a subtype of its upper bounds. So you have to iterate over all of its lower bounds to constrain them to be a subtype of the upper bound. And so this decomposes all of the constraints into constraints on variables, either in the upper bound or lower bound of a type. And so this is what this ends up looking like. At the top, we have one sort of iteration of this. And at the bottom is the results for our example. And you can see that we've aggregated sort of the pointer capabilities that were observed on StackSort2, and that we've sort of captured the recursive structure because StackSort1 points to StackSort2, and StackSort2 points to B, which then points to T1, and then T1 points to StackSort1. So we're going to see that we're going to end up with a recursive structure on this field. Once we have the constraint set, then we need to actually do that coalescing that I mentioned. And the way that you do this is you just introduce the constructor whenever you encounter a constructor. And the interesting case is when you hit a variable. So you need to perform a substitution at that point, and you just substitute in, I'm going to ignore recursive variables for a second. So you just substitute in each coalesced variable or each coalesced bound, either aggregating them by union or intersection, depending on the polarity position that you're currently in. And then for recursive variables, you just have to do an occurs check here to figure out if you're going to bind a recursive variable, and then you track a close set to figure out if you're working on a recursive variable. And so that's the type that you get at the top. It's a type. It's not very informative, though. The real trick of algebraic subtyping, right, is that since you've introduced intersection and union types, you can kind of read off your constraints into a type. And so this isn't very useful unless you simplify it. So we need some sort of simplification procedure. And the way this works is you lift into an automata and then apply determinization and minimization. And then you need to introduce a lattice on each node to figure out what types can be instantiated at that node. And then once we have a simplified automata, we can actually decompile it to like a sensible C type. So this is the automata construction. You're going to have a state for every single sub-expression of the type. And then the labels are parameters to those types. So if you see like the pointer example, for the store label, we're going to connect it to the state for the store parameter. And then sort of the interesting bit is that we need to label each of these states to keep maintenance on what types can be associated here. And so this is what the actual lattice ends up looking like. So first we label them with both the polarity and a lattice element, and you'll see why we need that in a second. And then the lattice is just a product of power set lattices, kind of, except for the atomic lattice, which is some parameterized lattice. And so you can see the first set is the variables that can be instantiated, then input parameters, output parameters, record capabilities, whether we can have a pointer here, and then finally those atomic-based types. And so this tells us what types that we're going to need to aggregate at this node. And when we're labeling initial nodes, we can just see what type syntax this was representing and introduce the capabilities into the lattice accordingly. like I said, since these are a bunch of power sets, we can just take, for a join, we can just take the intersection of each of these sets, and then the join on the atomic lattice, and similar thing for the meet. And then this admits, depending on the polarity, 2 different merging functions, either taking the join in the output position or the meet in the input position. And so when we actually go ahead and apply this to our example, this is the simplified automata that we get, and you can see on each of the nodes, we have these labels that we're maintaining. So in this sort of root node, we've maintained that this is going to be a pointer, and then that indicates to us that we're going to have to aggregate the load labels and the store labels for this type. And then the record label indicates that sort of we have this recursive structure here. Once you have an automata, we need to lower this to an actual C type. And what I'll say here is at this point, everything is sort of within the type system. Once you introduce lowering to C types, you have to be heuristic because you can't represent all bin sub types in C types. And so the way this works is you first have to break loops by consuming SEC edges. And the way that you want to do this is you identify pointer edges that point to nameable nodes, because those can be represented by just closing off that edge and pointing it to a synthetic named node to make a DAG. And then once you have a DAG, you can just go up the leaves, assigning types to nodes and merging as needed with some identities. These are the identities that you can use to merge. The most interesting one is the pointer identity. If we're intersecting 2 pointers, then we have to take the intersection by covariance of their output parameter or their load parameter, and then the union of their store parameters. But there's also this additional condition that we have to maintain, that the store is a subtype of a load, so we intersect it with those types there. So that wraps up roughly how type assignment works. So I did want to briefly highlight our formal results here. So we compared it to ret type D, and if you squint at it, everything looks like we're doing very similar things. And it turns out, yes, we are doing very similar things in preserving derivations. And the way you can see this is by relating the typing rules of ret type D to bin subtypes. And so this is just examples of how you translate ret type T type to a bin subtype. You can say if we have a load capability, then we can type it as a bin subtype. If we have for the variable a bin sub pointer type and we have that pointer rule applied. And I'm not going to go through sort of the proof sketch here, but I'm just going to highlight one rule and the how they relate to the field rules for ret type T. Roughly, you can see since it abstracts over covariant and contravariant parameters, we have to relate the covariant rule to the covariant portion of our pointer rule and the contravariant to the contravariant portion. And sort of the theorem that we're looking for is that if there's a derivation implied or entailed by a constraint set on ret type D constraints, they should be preserved in the bin sub translated constraint set. So here's our results. So we implemented this type system in Anger in their pre-decompilation analyses. We basically added an additional type solver that lifts ret type D constraints into bin sub constraints so that we can have a direct comparison. We use the all-star dataset, which is a dataset of binaries with dwarf information, so we have ground truth for the C type signatures. And then we used a type distance metric that is basically the lattice distance between types to see that we're preserving precision. We ran 7 micro benchmarks per function, and we retained only functions where we got micro benchmarks for both tools, all 7 micro benchmarks. And that leads to us filtering out some functions that you can see at the bottom there. Here's some statistics about the complexity of those functions, but moving on to the second table, you can see that, as expected, the average type distance is pretty similar. There is some variation in here for lowering heuristics and simplification, but the average runtime is substantively smaller, and that's just seconds over functions. But if we go to this slide, we can look at instead taking the pairwise mean percentage improvement. So the way you compute this is for any function, you take the percentage improvement, and then you bootstrap a distribution to get an 87 to 88% mean reduction in runtime on a confidence interval of 95%. And so these are the 2 figures of just plotting runtime versus number of constraints. So just to conclude, you can capture all of the features that you want for binary type inference in algebraic subtyping, and you can do it efficiently. And one way to look at this result is we can get an efficient algorithm for binary type inference, and that's kind of cool. But what I more want to stress is that we have an efficient translation from binary type inference to algebraic subtyping. So that means that we can start looking for connections between high-level type inference and low-level type inference for more sort of research synthesis in that area. And that wraps up my presentation. Thank you.
Thank you for your presentation. Questions? Take.
What is your notion of correctness here?
So there's sort of two things that you can say about correctness of binary type algorithms. Are you correct with respect to your type rules for whatever your type system is? And then relating that to C is a separate question. And so insofar as the constraint set is concerned, we can say we're sound with respect to the type rules that we have for bin sub. With respect to C, like I said, you can't represent bin subtypes in C. So there's no soundness guarantees once you lower to C types. So essentially what you're saying is the pre-static analyses produce some sound over approximation of the behavior of the program. Then you can relate that to your type rules and your bin subtypes. Once you go to C types, you're breaking your soundness guarantees.
Any other?
I'm curious, what's the full list of atomic types you reference?
There's a lot of them.
I
don't know all of them, but there's at least like basically integers. Then you have subtypes of those for size of integers, and then you have sign types, etc.
So have you thought about this like more quantized type, like a smaller bit?
Sorry,
a quantized type, like bits 16, int 16, and
so
those things.
There is like an int 16 and like a char type in your type lattice. I don't remember the exact atomic types in the type lattice off the top of my head.
Okay, thanks.
Any other question?
Yes, I was not sure if your type inference algorithm was flow sensitive, and if so, can you comment on whether flow sensitivity is useful for binary code analysis?
So insofar as flow sensitivity is important, usually this is encoded in, at least how I've observed them encoded in type inference algorithms, is you're going to be looking at connecting uses to definitions with registers by reaching definitions, rather than saying like, we don't ever want to say that all instances of EAX in this program are like subtypes of each other, because like I can guarantee to you, right, like a pointer to something and an integer to something is going to be put into EAX at some time. And so that's usually how you see flow sensitivity, and you'll also encode flow sensitivity in whatever pointer analysis you're doing to resolve your stores and loads, is typically how I'd see that done. And then for insofar as the type system itself, the only sort of flow sensitivity that you have is that you're maintaining separation of facts via subtyping, rather than making the relation reflexive, so that you end up joining stuff that was not spuriously supposed to be joined.
We have time for a last question. No? Okay, let's thank the speaker again. Okay, the second speaker is Kimball Germain, and the talk is full control flow sensitivity for definitional interpreter. Okay, you can start.
Sorry, there's a lot to manage here. Okay, thank you for the introduction. I'm going to talk about full control flow sensitivity for definitional interpreters. So I want to start by talking about three basic notions of control flow sensitivity. We've got flow insensitivity, or actually let me start from the right. Path sensitivity in an analysis produces a solution for every path point. Flow sensitivity produces a solution for every evaluation point. And flow insensitivity produces a single global solution. And I've ordered these on the slide from least to most precise. So what I'm going to talk about today is a framework for writing definitional interpreter-based analyses in which you can express each of these sensitivities, as well as a few more that we'll see later. So just to establish a baseline, I want to walk through some different sensitivities. And this program on the left, we're going to look at quite a bit, so it's worth taking a little bit of time to get acquainted with it. So we have three variables in this program, n, x, and y. The value of n is established before this part of the program begins. And every branch in the program is on whether n is 0 or not. So in a path-sensitive analysis, we have a solution for every path point. And so the analysis quickly discovers there are two paths. And we've got one path where it discovers that n is 0 and is able to determine that x must be 1 and that by the end y must be 5. So it perfectly correlates the values of n, x, and y. Similarly, in path 2, when n is not 0, we have the same discovery that x must be 4 and the correlation that x is 4 and y is 6. In a flow-sensitive analysis, where we have a solution for every evaluation point, the paths of the evaluation are not considered per se, but instead we use where we are in the program and can refine based on that location. So at program point 3, we know that n is equal to 0, whereas in 4, n is not equal to 0. And you can see that by the end, we are not able to precisely correlate the values of x and y. And so it's slightly less precise than a path-sensitive analysis. And of course, a flow-insensitive analysis, there's a single global solution that must subsume all of the facts at any individual point in the program. And so we have no correlation at all. So this is our baseline for these control flow sensitivities. Now, our work descends from a work on modular abstract interpreters by David de Reyes and some co-authors. And this work reflects the control flow sensitivity of the analysis in the state space of the analysis. So a path-sensitive analysis allows you to express path sensitivity by relating evaluation points and fact bases B. Flow-sensitive analysis, that's manifest as a map where for every evaluation point in the analysis you have a fact. And then a flow-insensitive analysis where for you have a set of evaluation points, and then off to the side you've got a single fact base. And so in this framework, the control flow sensitivity is entirely contained in the structure of the state space. Now, that work, the modular abstract interpreter's work, was done in the small step setting, but we are in the big step setting as we're working with definitional interpreters. And thank you. And in this setting, the base analysis has a different structure. Rather than talking about a set of program points, we are talking about a what we'll call a cache from configurations, evaluation configurations, to their results. And so there's a shift in perspective that we need to make from facts describing points in evaluation to facts describing something about the evaluation of an expression or a summary of the evaluation of an expression. So in this work, we do the same move that modular abstract interpreters does, where we want to reflect the control flow sensitivity in the state space. And so, once again, for path sensitivity, in order to introduce a path-sensitive quantity B, we need to associate it both with configurations and with our result values, and we need to allow arbitrary relations on those. I'm going to move over to flow insensitivity. Here we just have a global fact base that's off to the side of our program analysis. Now, flow sensitivity is interesting because what we're going to do is associate with each configuration two fact bases. One, this one here, represents the fact at the beginning of evaluation of the configuration, and this here represents the facts that hold at the end of evaluation of that configuration. And this is a new notion that we introduce in this work. So here we've got the same program, and I've got a very different looking analysis. And that is because in a summary-based analysis, the analyzer is going to produce from a configuration both a result and the fact base. We also are going to change our perspective where we're not going to consider these line numbers here to be labels for program points, but they're rather labels for program expressions. So the entire expression has label 1, and as another example, this is not program point 5, but this 5 labels this expression 5. So we won't walk through both paths in excruciating detail, but if you look at the end, you can see in each path that the resulting fact base represents the perfect correlation that we saw in the small step example of this program, and that this final result is subsumed in the result of this enclosing expression, and so we see the final result propagated to nesting expressions. So the point is that the notion of path sensitivity that we have in the small step setting and the big step setting are the same. And this is standard, but things are going to get a little more interesting for us right now. And that's because, as far as I'm aware, there's no notion of flow sensitivity in the big step setting or in the definitional interpreter setting. And so this is the notion that we introduced in this work. So these circles here, these circular nodes, represent configurations. The square nodes represent results. And the quantities inside represent the value of the fact base at that point. And so what we have here is a configuration that results in some result. So this summarizes an evaluation segment. And every evaluation segment that contains that segment as a subsegment, the initial value of C is going to contribute to the initial value of the subsegment. And then once the result of the subsegment is obtained, then the resulting value C is going to be propagated and might be refined as that path or that sequence joins back with the super sequence. So this is the notion of control flow sensitivity, or of flow sensitivity that we have in our framework. So once again, we have an analysis, a flow-sensitive analysis, where we have a fact for every entry and a fact for every exit. And the important thing to note here is that we get the exact same correlation that we did for a small step flow-sensitive analysis. So this notion of flow sensitivity for a definitional interpreter matches up with our expectations from a small step interpreter. Okay, so our framework allows us to integrate all of these notions of control flow sensitivity. So throughout the rest of the examples, we're going to see some quantities. We're going to see quantities V, W, and Y corresponding to path sensitive, flow sensitive and flow insensitive fact bases. And U is going to be a per path component capturing an aspect of the continuation. This is like, you might represent your environment in your configuration with this, or maybe your timestamp. And if we integrate all of these notions of control flow sensitivity in the state space, we end up with this very gnarly looking state space. And this is sort of the base state space of our framework, where we can instantiate this state space to realize control flow sensitivity at any of the sensitivities we've talked about, and we can do it simultaneously. Now, I'm going to shift now in the talk from this state space. We're going to talk about how can we effectively write analyzers that produce something in this state space. So we're going to talk about instantiating definitional interpreters in this framework. Okay, so what we do is we take the language from the modular abstract interpreters framework. And it's a simple functional language with some basic primitives for arithmetic and such. And this is the language we're going to use for examples, but our framework doesn't have any specific limitations when it comes to languages. There are no features that we have specific problems with. We're not going to talk about mutation, but our framework handles mutation fine. So let's shift our attention to this here. This is the core of a definitional interpreter. And it's a pretty standard interpreter, but there are a few things we want to note. So the first is that this interpreter is written in terms of this type constructor M, which is a monad. And so we get to write this interpreter in terms of how it evaluates an expression and produces a value. The second thing to note is that it's apparent from the type and from the term here that this interpreter is open recursive. So that means that every apparently recursive call in this interpreter is actually just calling the argument eval. Within the implementation of this interpreter, there are some primitive effects like we've got like extend in environment, and I think there's a lookup in here. And these are effects that access components of the configuration. So we've got, for a given interpreter, part of its implementation is definitions for an allocation function, a lookup function, a way to extend something in the store. And these definitions are also monadic. And are in terms of some basic effect operations like getting the store and getting an environment variable. A few other things we want to mention about this interpreter. One is that when we take an abstract value, we need to turn an abstract value into a finite set of observations in several cases. One case is when we want to apply a function. We need to obtain a finite set of possible functions to apply. And another is when we ask whether a particular abstract value is 0 or not. We want to determine the set of truth values for that predicate. So part of the implementation is an elimination function that allows us to make these observations. And then we assume that we have this operator here, this up arrow, which will turn a finite set of observations into a non-deterministic monadic computation. Finally, I just want to make one more comment about this tick function. So in some work, context sensitivity is folded into control flow sensitivity, and it is not in our framework, at least not yet. So that means that our interpreter hard codes the context sensitivity of the analysis. And in this case, we're using call site sensitivity, and we have slightly abstracted this so that our particular definition of tick here will use a kind of call site sensitivity where the context is represented as the stack, or the top portion of the stack, and we can change the definition of tick to recover something like KCFA, where we use the last, the most recent call sites rather than the stack frames. Okay, so the interpreter allows you to talk about evaluation in terms of expressions and values. But underneath the interpreter is a caching interface. And that caching interface is in terms of configurations and results. And we have this caching interface so that we can basically implement back-end caching strategies that are independent of the interpreter. And part of the definition of an interpreter is just some functions that allow you to go to and from the interpreter space and the caching interface space. And they're really just plumbing functions, but they're necessary to make the translation. So in the paper, we present a naive caching algorithm. And so a caching algorithm entails a definition for configurations and results, what those look like, and then a monad that will basically plumb all of the appropriate quantities where they need to go. So I just want to describe in high-level detail how the naive caching framework works. So this monad is going to take a flow-sensitive and a flow-insensitive quantity, and it's going to take a cache that for previously seen configurations produces the known results and the known flow or flow-sensitive quantity when those results were obtained. It's going to produce a set of results, a flow-sensitive quantity, a flow-insensitive quantity, a set of scene configurations, and a new association between configurations and flow-sensitive quantities. Now the point here is that this type is both pretty gnarly, and it's really just an artifact of the particular approach to caching that this algorithm takes. And we are able to put it in this framework because we, the framework has the capability to handle something really just kind of as ad hoc as this. And then just a little bit more detail about how this caching algorithm works is we've got this execution function which wraps the evaluation function, and as you'll recall, this function is open recursive. So we need to pass a function in that will be called on recursive calls, and we pass in this stub function that actually doesn't do evaluation. It just records quantities that it has seen for the next iteration of the caching and returns a known result. So we discussed this algorithm more in the paper. But the point here is that there are many different algorithms that you could implement, and the interface is fairly thin that is required by our framework. Okay, when you implement one of the a caching strategy, caching interface, it's monadic, so you need to also implement some monadic operations. You need the, of course, return and bind. We also require you to have non-determinism and some state effects. And if you have state effects for the flow-insensitive and flow-sensitive quantities, you can usually put those just in terms of your simple return and bind. Okay, with all that in place, so you write your definitional interpreter hopefully once, you write a caching strategy hopefully once, and when you actually want to instantiate an analysis, it's very simple. You simply need to select the sensitivity at which you would like to treat each analysis quantity, and that is done through some definitions where the concrete definition for getting the store is put in terms of which state effect, which particular state effect you're going to access. And so a path-sensitive analysis would simply define getting the store as getting the path-sensitive state, whereas a flow-sensitive analysis is not shown, but it would be getting the store as the flow-sensitive state. Okay, I wanted to briefly talk about analysis validity, how we, what we consider to be the ground truth of the analysis and how we show that. So we consider the ground truth to be an evaluation carried out where every analysis quantity is treated path sensitively. And so we have the state space for configurations and results have all of these quantities path sensitively, and there's a corresponding monad, which I will not go through, that maybe I'll go through it a little bit. When we evaluate, we keep track of the results that we obtain and the configurations we encounter, and then we record results to their configurations as we encounter them. So we can see that down here in this program evaluation section, that when we execute, we make our recursive call, and it's going to give us a result. It's going to give us some scene configurations, and it's going to give us a cache. And we're simply going to join our results with that, so that as we evaluate, we're just keeping a record of everything that's gone on. And then the semantics of a program are the limit of a join where we take the limit on n, where n is the recursion depth that we allow the analyzer to, or the evaluator to go. So this is an incomputable semantics, but we use it as our ground truth. So if we have an analysis that produces a set of scene states, our flow insensitive quantity, our results, and our, flow sensitive quantities, flow insensitive quantity y, and we have some evaluation, which is a set of configurations and results, and a cache of results, then we can relate them. And just as an example, you would expect that if you have a flow insensitive quantity y produced by your analysis, that if you were to look in every configuration and every result of an actual evaluation, that this y should subsume them. And so that is one of the conditions, or two of the conditions, of analysis validity. And we use this, this definition of validity to show, or we build our theorem that our caching strategy is valid on this definition. So we did some implementation work in the paper, and the purpose of the implementation work was basically twofold. The first was to show that the framework was capable of handling different caching strategies. So we implemented the naive, which I have discussed. The co-inductive caching strategy is a strategy that was presented by the abstracting definitional interpreters work, and a dependency tracking is based on a fixed point solver. So the framework can really handle a variety of caching strategies. The second purpose was to at least verify that the cost of different sensitivities matched our intuition in this setting, the intuition that we gained in the small step setting. And so you can see that we're comparing sensitivities across here, and each line represents 2 orders of magnitude. And so as you would expect, as you treat things with less sensitivity, the cost goes down. And so our notion of flow sensitivity that we introduced in the paper follows our expectation for about what it should cost as we've gotten it from the small step setting. Okay, just one final aspect here. So the abstract definitional interpreters paper is kind of a sequel paper to modular abstract interpreters. It allows you to write abstract interpreters using definitional interpreters. It uses monads and monad transformers. Our work is very much inspired by it. And I want to talk about kind of a feature present in that work that was taken from modular abstract interpreters. So modular abstract interpreters takes sort of a base analysis form, like a point, and it applies state space transformers to it. And so if you take this point and you apply a state transformer, and then you apply a non-determinism transformer, you end up with this kind of state space, which reflects a path-sensitive analysis. If you do the same thing but in the opposite order, so first you apply the non-deterministic transformer and then you apply the state transformer, you obtain this state space, which is a flow insensitive state space. This same framework, or the same framework, is present in the definitional interpreters work, the abstract definitional interpreters, but the effect is not the same. So when you apply state and then non-determinism, you obtain this state space, which is path sensitivity, but when you invert the order, you obtain this state space, which does not correspond to any sensitivity we've talked about. In particular, you've got path sensitivity in your configurations, but you've got flow sensitivity in your results. So we situate this in our hierarchy, and we call it result widening because the result is more widened than the configuration. And there is a big state space that I could put on the board that integrates all 4 of these sensitivities. That is in the paper. So we are able to fully account for what abstract definitional interpreters does, as well as fully account for these other notions of sensitivity as well. So in conclusion, this work introduces a notion of flow sensitivity for definitional interpreters, allows us to realize a range of control flow sensitivities simultaneously, has a semantics independent instantiation, which I did not discuss much in this talk, but you can read about in the paper, and uses monadic abstraction, which really allows us to separate the different components of the analyzer effectively. Thank you.
Thank you, Kimball, for the talk. Any question?
I have the impression that you assume that the abstract domain satisfies the ascending chain condition.
Yep.
And also, when you have infinite paths, I wonder if even you need finite domains.
Oh, yes. And so in the paper, we talk about for each component specific requirements we have on them. And yes, one of them is finite domains for the path-sensitive components, the ascending chain condition for the flow-sensitive and for the flow-insensitive components. And then even for the definitional interpreter component, it's a functional interface, and we require that the function is monotonic in every argument, essentially.
Okay, so you need more work.
Need more work?
Yes, maybe next year you have one that handle any abstract domain, relational domain,
all right,
and so on.
Yeah, we can always improve.
Any other question?
You talk about selecting the sensitivity, but I got the impression that your definition sort of would imply that you select the sensitivity before you do the analysis. In other words, will your approach support analyzing a single program with different sensitivities at different parts of the program?
Oh, yeah. Thank you for asking this question. Yeah, let me go back. So selecting the sensitivity, I kind of gave the simplest possible definition you could give, but it's possible to use like an introspective definition here, where as the analysis runs, you are deciding what component that you're going to provide. And we haven't explored that a lot, although we have explored the idea of, partitioning maybe like the store or something at different sensitivities based on the program. But yeah, that's something that we are exploring.
Any other questions?
So I think on the slide for the monad abstraction, a few slides after that.
Or was it that or that?
I think, no, I think you mentioned a thing about when we're concretizing with the monads, we do it non-deterministically. Could you explain that again?
This slide?
Yes.
Okay, so I did not mention that we are parameterized by our value domain. And depending on your value domain, well, we require an interface, a way to take a value from the value domain and turn it into a finite set of observations. And so if I understand your question, it was really that when you define your value domain, you also need to define this way of making finite observations on the value based on these operations we require, which is we're going to call a function, so we're going to make a closure observation, and we're going to branch, and so we're going to make an is0 observation. Did that address your question? Okay, great.
The last talk of the session will be given by Sparse. And the talk title is trace partitioning as an optimization problem. So you can start.
Where's the Sorry for that. Hello, everyone. Now I'm Charles, and today I'll be talking about our work, which is titled Trace Partitioning as an Optimization Problem. And this is joint work with Matthew Lemaire and Sebastian Burden and Jean-Yves Maria. And okay, so there are several sources of imprecision in static analysis. And where does imprecision come from? Firstly, like not using best abstract transformers, and secondly, primarily due to incompleteness of best abstract transformers, and thirdly, using the abstraction itself when it's not precise enough to prove properties, and fourth, like when composing the abstract operators, you also have imprecision, and fifth one, primarily what we will be focusing is more about the non-distributive domains where joins also inject imprecision in the analysis. So how do you solve the imprecision? The well-known idea is to develop more precise domains or more transfer functions, but you know, it's really quite challenging because people spend a lot of years developing good domains. And the other approach is trying to use generic method based on trace partitioning, which I'll be talking about today. So here is a code, which on the left you can see where x is modified in two different ways. X is equal to 1 and x is equal to -1.
and you want to assert in the end that x is not equal to 0. So if you just use plain interval analysis, when the results are joined after the conditional statement, you get -1 to 1, and then so you no longer can prove the property. On the other hand, if you take the partition state where you keep the values of x separate, where you have x now no longer contains 0 in it, and now you can easily assert that x is not equal to 0. So unfortunately, there are two problems with trace partitioning, where when you have too many disjunctions, this leads to path explosion. You see the program on the right, where you have sequence of conditionals, and if you split too much, this leads to path explosion. And the second problem is if you use too few disjunctions, you may not improve precision. It's the same program between if then else and assert. I added some unnecessary code, and if you just use interval analysis, and of course, like when you merge the value of x, you will have -1 to 1, and so you can no longer prove the property. But on the other hand, if you use the partition state, where you split for some time, and if you don't know how long to maintain disjunctions, and if at some point you merge the analysis, you get x from 1 to 1, and again, you can't prove the property. So if you use too much, you lead to path explosion, and if you use too little, you may not improve precision. So the classical method for trace partitioning is to use heuristics to obtain some trace partitioning that balances, like trying to improve precision, but not leading towards path explosion. And the question we ask is, how do you find suitable trace partitioning that improves precision and avoids path explosion? So the main contribution of our work is to develop a search-based method to find an optimal trace partitioning. And there are couple of contributions here. One is we do search-based quotienting, which I'll talk about a little bit later. And then the ratchet search about continuous improvement of precision. And thirdly, incremental computation. And fourth, we'll talk about dealing with non-monotonic operators and also the lessons learned. OK, I'll motivate with an example. Here you have the program on the right. And we want to use analysis like using constant propagation. Here you have two variables, x and y, and you have an error location, which is, although not reachable in the concrete, it is, the analysis says it is reachable in the abstract, where you have x and y as top, like you can see in the bottom. So the program is, we did not prove that the program is safe, and let's say if we do make some splits in the bottom, as you've seen here, we do improve precision. Now the precision at the error location improved from top to 1 to top, but still it is not enough. Let's make some more splits like I've done here. Now we managed to get the bottom state at the error location, and that we proved the program is safe. But we asked the question whether it is optimal. In fact, it is not optimal because now we can undo the split that we have done before, and you still maintain the same fixed point state at the bottom at the error location. And now the program is safe. So you saw an observation here is that if some newer splits can make older splits also useless. And so as you've seen here, we have this, for the original program, there are several refinements. Some improve precision. Among them, some improve properties. Among them, some are more optimal. So how do you find these optimal refinements? Given that the search space of possible refinements of the original program is quite large and mostly graphs, like searching among the graph is quite hard. So the first contribution of our work is how do you quotient the search space, and we do it with using tuples. What are tuples here? So take the program on the right, and here we a priori select some split points, which I highlighted in star, which has multiple incoming edges, and which we want to separate. And now we take it, so since we selected 3 points, we have 3 tuples, where the dimension is 3. And we associate each dimension to a split point. And now, since we have tuples, there are certain operations we can perform on tuples, which are, for instance, successor operation, like I will do here. So if you apply successor operation on the third component, you get 0, 0, 1. This exactly corresponds to this successor operation has a corresponding delay operation for the third split point. As you can see, I delayed the third split point by 1 step here. So, of course, it did not improve the precision. It's the original example itself. So we'll try with more splits. And we'll, here we can go from 0, 0, 1 to 1, 0, 1, where I'm now applied successor operation in the first dimension, which means I will be delaying the first split point at the top, which now says that the error is unreachable. And finally, because it is not optimal, then we again undo the successor undo the successor operation that we did at the third dimension, and we go from 101 to 100, which means we have a corresponding merge operation on the graph, and the program is optimal now. So what we have shown here is that in the paper we show that there is a homomorphism between these n tuples and the CFG refinements, and more details are in the paper. And in fact, because searching in the graph space is quite hard, and now we can do it in the space of tuples, which is much easier to deal with. And so tuples provide an approximate measure of precision in the graph size. So if T1 is less than T2, then in fact the HT2 is kind of a refinement of HT1, and which means you refine HT1 itself, and the program size is also a bit larger. And when you do fixed points, when you compute fixed points on the HT2, and it is at least as precise as HT1. A small caveat here, we assume that abstract operators are monotonic, and we'll talk about non-monotonic operators a bit later. And an important observation is that if T1 is less than T2, it means that the graph corresponding to T2 is strictly larger, but possibly equal in precision. So this leads us to something called this is two-phase search, where in one phase we can improve precision, and in the other phase we can find a minimal program which has an equal precision. So you can see that in the picture on the right. So when we improve precision, we are making some splits, which means we are this is the precision axis, and that is a program axis. When we improve the precision, we are going up in the program size as well as in the precision axis. And then when at some point, when we go to the minimization phase, we try to maintain the precision, whatever we had before, and try to shrink the program size using the merging. So, and you do this in alternate phases, and then you improve, merge, and you improve, merge, and you improve, minimize, and so on. This is the trajectory you get on in the search space. And this is how we do the search to improve trace partitioning. And the algorithm is anytime, because anytime you have, if you're satisfied with the precision you have, you can terminate with that particular refinement. And what does equal precision mean here? Because when we have some set of, when we have two refinements in the search space, what does it mean for them to have equal precision? Here I have the same example, but I removed the assertion and added some useless code. Again, if you do interval analysis, X will be -1 to 1. And on the partition side, if you try to keep the value of X separate, but you see that I kept it separate until the end. So you can see that splits do improve on useless control locations, but it's not something we don't want, because a fundamental insight of our work is that we aim to improve precision at some locations of interest. For instance, these are assertion points these are, for instance, locations which have unproved assertions. And the important consequence of selecting few locations of interest is that whenever a split is no longer contributing at the locations of interest, we can now merge it. So that's what I've shown in the earlier example, where the split is no longer contributing at the error location that I managed to merge it. If we try to improve at every location, then what ends up happening is we go up in that, we never come down, and we just keep going up, and we go to path explosion. And when we are traversing the search space, going from one refinement to the other we should not do like, okay, when we're going to the other refinement, we don't want to compute the whole graph refinement from scratch and don't want to do whole fixed point computation on top of it because it's quite expensive. How do we mitigate this? We use incremental computation. For instance, when we do a transformation, we are just locally changing the graph at few points in the program, few control locations. So these transformations are imperative on imperative graph, and now we just only remove parts of the fixed point map that where we have to recompute, and we don't have to recompute for everything. So you can see I just dropped 3 states here, and then I can recompute them like this. And then, okay, when we apply another split, we just locally change the graph, modify the graph a little bit, and then we recompute the states again there, like this. And when we go there, we don't have to recompute the other states on the left because the state at 3 did not change. So the only only state changes that I need to do are the on the right-hand side because the state at 8 changed, and so we have to update this one and then this one, and then we prove that there it is unreachable. So this is what incremental computation allows us to, because it's very cheap in nature, so it allows us to test several thousands of refinements in seconds. And another one is the tuple exploration strategy to improve precision. First one is pruning. Let's say if a tuple 3, 4, 2 is not improving in precision, then we can in fact we don't have to explore all the tuples which are smaller than that tuple itself in component-wise ordering. So, which means we prune all the downward closed elements of that tuple. And next one is the priority exploration. And one of the insights is that it's important to explore one dimension at a time first, because firstly this has a smaller search space because now you don't have to do like trying to improve 2 dimensions at the same time, or 5 dimensions at the same time, or 10 dimensions at the same time. But improving 1 dimension at the same time is actually enough. And for the programs which do require multiple splits, what we have observed is the following. So let's say there are 2 splits, and at the locations of interest you have precision D, and let's say you make a split here, and it in fact improves, let's say it improves D prime, and since it improved at locations of interest, we keep that split no matter what now. And then let's say we do another split, it does further improve to D double prime. So for the programs which do require multiple split, we can in fact get through, we can actually get there by just sequentially exploring the dimensions. And this actually reduces search space significantly. And finally, we also have to address non-monotonic operators. Let's say you have the program on the right, just don't have to focus on it. And there is a, let's say, previous refinement, and then there is a current refinement. And let's say, basically, the current refinement you obtain by splitting somewhere, which happens at, which I'll show. Just focus on the states which are in color. So in the previous refinement, x is 1 to 160, 1 to 60. And when we make a split, x becomes 1 to 1 or 60, 60. And actually see that now the abstract state of the loop head completely worsens compared to what we had in the previous refinement. Okay, it doesn't get worsened, but it becomes completely incomparable. Previously you had -40 to infinity, but now you have -infinity to 1. So because we're trying to monotonically improve precision, non-monotonic operators are a bit tricky because the current refinement can have really incomparable precision with the previous one, or the worse precision even, for instance. So how do we solve this? Instead of, a naive solution is to basically discard the current refinement and just focus on the refinements which lead to better improvements. But in our work, what we try to do is we have a nice trick called forcing monotonicity. So these 2 states, as you can see, -40 to infinity and -infinity to 1, they're in fact sound approximation of reachable states themselves. So what we can do is, in fact, we can take a meet of them. Meet is, in fact, even a sound approximation of reachable states. And then we can force that new result in that current refinement. Now, in fact, that this becomes much better. In fact, we improved the loop invariant itself there, and this is how we do. This is how we force when you have non-monotonicity, doing some tricky things. So to summarize, when you have monotonic operators, incremental computation, when you incrementally arrive at a refinement, it yields same results as doing whole fixed point computation on that refinement. But when you have non-monotonic operators, incrementally arriving at a refinement can yield at least as precise or even more precise than doing whole fixed point computation on that refinement. So, and the invariance that you get by doing incremental computation really depends on the exploration path taken. Because these invariants may not be inductive, or may be inductive or may not be inductive, so how to reproduce them? You take the exploration path and you can reproduce those invariants. And finally, we have the evaluation where the analyzer is written in OCaml, and we use SV-complete safety benchmark with programs and its details on the paper. And as for the domains, we use Acron library and we don't implement these famous domains from scratch again, and we just use the library, and then we also add constant propagation and the product of intervals and congruence. So conclusion, it's actually, so on the x-axis you have the number of property instances, on the y-axis you have the computation time. For each program we give like a 1 hour timeout. And we have three baselines. One is the no split where we do not do any trace partitioning, and full split where we do full trace partitioning with k is equal to 1000. And the usual heuristic, which tries to split everything incrementally, is what we use for third baseline. And our primary algorithm is IDDDS, which is kind of iterative deepening depth first search based algorithm, and it outperforms. It proves a lot more properties, and these baselines time out, like at least no split and full split time out quickly on a lot of programs, and it's also much better than the standard heuristic SDS. And on the other side, on the next one, we have that the approach is agnostic of the domain, where we take these 4 domains, which are mainly taken from Apron, and we add constant propagation. And basically, as long as the abstract operator implementations are given, which is just widening or inclusion or join, just basic operators, and you plug in and you can use the refinement. So as you can see that these domains, and as you can see, like a lot of these domains do much better with trace partitioning than without trace partitioning. So, and other one is we have incremental computation. We show that incremental computation is actually quite useful, and that it really outperforms the non-incremental for the programs at least which it can get. It is worse in terms of the number of transfer functions computed. So that is y-axis is the number of transfer functions computed, and the x-axis is the property instances stalled. And incremental one outperforms by 100 times, and for the programs which non-incremental gets, and even non-incremental times out on a lot of benchmarks. And finally, we also have a combination of different sensitivities, where we take, in this paper we have implemented 3 tuple encodable transformations. One is joint splitting, and other one is loop unrolling, and other one is context sensitive. So each dimension can be any of these 3 things. And in fact, we showed that combining different kind of transformations proves significantly more properties than using a single kind alone. And finally, to conclude, we tackle the challenge of automatically tuning the trace partitioning by casting it as an optimization task, and we provide a search-based method to solve it. And I think it's quite useful and quite easy to plug in any existing static analyzers and to improve precision. And it is available as an artifact. Thank you.
Thank you for your talk. We have time for any questions.
Hi. Maybe I missed something, but can you motivate your pruning again? Because it seems like you've already done the analysis with the split graph. So why do you want to prune it? I mean, you've already done the analysis. Or is it something where you're analyzing the same function again and again and you preserve the split?
Oh, let's say when we have explored the tuple 342.
No, it's not this one. You had this other graph where you were talking about the program size and the that one. And then you sort of unsplit, right? You
here.
You merge. Yeah, yeah.
So when you do go up like this, you split, you perform transformations. And then here you undo the splits.
Right. Why?
Because if you don't, then you keep going towards, you go up and up and up, and you go to path explosion, which is something that you don't want in the first place.
But how do you decide?
So this is what I've shown in this example here, right? So when you merge this branch and you recompute the state again, you will end up having the top. You will end up having the bottom. So it's increment. So you merge, you try to merge and see what you get, the result. And if you end up having the same result, which means you can merge it. Yeah.
So sorry. So the precision that you're measuring is some sort of local, like you're unsplitting or merging to maintain some local precision.
Yeah.
And okay,
sometimes it can be like this. For instance, your location is somewhere.
Right.
But let's say when you merge, it may not, it may worsen the precision. But when you propagate that, you can end up having the same one too, at the locations of interest. So what you care about is the precision at locations of interest. Here, the location of interest is this one itself. So when you merge, you check the result here, and it's the same top. It's the same bottom.
Right. I think
So
my question was, I think, answered.
Okay.
So we've been talking about merging, and I'm sorry to go on about merging, but in the paper, you mentioned that the merge function rarely runs. Like, you rarely find a tuple that actually maintains precision and reduces the size. Do you have an intuition for why that's occurring, or why there isn't some equivalent smaller graph?
I think my intuition of it is that when you have locations of interest, which is quite small, like if just one location here, usually when you have a lot of locations of interest, that's when you will really need merging. But if you just have very few locations of interest, merging is usually not useful. But I can give you more details about it.
If you push partitioning to the extreme, you get model shaking. That is, you get all paths one by one.
Yeah.
And so I understand you have two ways to avoid it. That is, first you choose the tuple.
Yeah.
How is all points where you have a choice, or you have some heuristic? No, all points.
So no. So at least in the experiments, we selected all the points which has multiple incoming edges, and then you can extend the tuple to even, you can dynamically add new split points into the tuple too, because you now start with a 0. That's
Okay.
it. Yeah.
And the other way to avoid this explosion is the undo.
Yeah.
And that the only two things you need.
Yeah.
Okay, good. Also, it's exponential or tower of exponential, the time.
What time?
The time that it takes to do the partitioning, I think it could degenerate in some exponential or even tower of exponential time.
Yeah.
Because the experiments are nothing, because an experiment is always constant time.
Yeah, sure.
So
yeah. So let's say if your property itself needs full path explosion, then there's nothing you can do about it.
Okay.
Yeah. But if you don't, then if you have an optimal trace partition which can prove the property of interest, you can necessarily find it.
So I was thinking you need some kind of widening in this process somewhere.
Widening. I haven't thought about that.
Where you decide not to go further. in the partitioning?
Maybe we can discuss it offline. I can't think of an immediate answer.
neural networks. So we have in program one tutorial and 3 talks. So we start with the tutorial presented by Caterina Urban. She is now a permanent researcher in École Normale Supérieure with INRIA in the team Antique. She got the PhD in computer science in the École Normale, the same team exactly, in the École Normale Supérieure in Paris. And she did the postdoc in the ATH with Peter Müller. She is now presenting a tutorial in abstract interpretation-based certification of hyperproperties for high-stakes machine learning software. Caterina, please. Thank you.
Thank you. Thanks, Roberto, for the invitation. Okay, so it's a tutorial. If you want the perspectives of the work that we can do in this space, you need to come to my talk on Tuesday at NSAD. Okay, so the title is very long, I'm very sorry, but what I want to talk about is, what I decided to do is to give you, to take a use case. In fact, it's a use case that comes from a collaboration that I had with a company. So they gave me this use case and they had to prove this hyperproperties of this machine learning software. So in particular, the use case that I wanted to present is a machine learning based air transportation software. So what we have, so in air transportation, the accidents are very, very rare, of course. But when they happen, there was a recent estimate that about 20% of the time, these are runway excursions. So essentially, you overshoot the landing, the runway during landing. And so these are 2 examples, a couple of examples, but of course there are many, many more if you look for them. This was in Florida in 2019 and in France in 2022. And based on this fact that a lot of the accidents are because of these runway excursions, there is a new regulation that was approved by the European Commission. So they should was supposed to starting from January 1st, 2025, but I think the deadline may be pushed forward to July 1st, 2026. But basically what this regulation says that the new airplanes, they have to be equipped with a runway overrun awareness and alerting system. What that means is that basically they need to have some system that alerts them when there is a risk of this runway excursion. The problem is that so the airline companies, they already have actually reference systems that can do these computations. They have basically simulations models they can use to do this. But the problem is that these require too much computing power or too much computing time. So they cannot be directly embedded into the airplanes. So it's actually one of the typical use cases where machine learning comes useful. Because then you can use this, the reference model, which is your ground truth, to train a machine learning model as a surrogate, basically, for this reference system. And then, since the machine learning model is basically a compressed version of it, you can embed it on the airplane and you can use it. So you can basically equip the airplane with this new functionality, but then of course you have to make sure that it does the right thing. So of course you don't want your neural network surrogate to recommend a landing when the reference model will recommend a go-around. And ideally, you also don't want to recommend too many go-arounds because this, of course, incur extra costs. So what I want to do is basically start with a toy example. I cannot show you the real network that I got, but so I can make a compressed version of it as a toy example. I will talk about safety first, because, well, that's the easiest thing that we can do. And then we talk about hyperproperties. So the toy example is basically something very simple. We can get some sensor measurements in input, the weight of the plane, the temperature, the altitude, the speed, the wind, the slope of the runway, things like that. And then we have a number of nodes in the network. I'm making it very small, but just so you can see. Each of these nodes basically is taking the values of the nodes in the previous layers. So this is organized in layers. These are the hidden layers, the ones in between here. And each one of these basically computes this linear combination of the values coming from the previous layer and applies an activation function. So in this particular case, I will talking about the ReLU function, which is essentially a max function. So either the linear combination is positive, and then it's the identity function, or if it's negative, it sets it to 0. Okay. After all these computations, in the end, we have basically, well, what the network originally computes is breaking distance estimation. So it estimates how long it will take for the airplane to stop, to come to a full stop. What I'm making, to simplify things, I'm making it as a classification problem. So I'm plugging in, the runway length. So I'm basically saying, if the braking distance is smaller than the runway length, then it's safe to land, and otherwise we have to go around. So I'm basically adding the runway length as a parameter of this this model. Okay, so this will be our toy example for the rest of the tutorial, and of course nobody will be shocked here if I rewrite this as a Python program. I hope it's okay. So I'm writing ReLU there, but it's basically an if then else. It's just otherwise it doesn't fit on the slide, this part at least. Okay, so at this point, since I have a simple program, I can treat it as a normal program and do abstract interpretation as usual. So I can start with the trace semantics, all possible executions of this program for all possible inputs. In the rest of the tutorial, when I talk about executions, I will use T0 like an execution T. I use T0 to represent the values of the inputs nodes there, and TW for the prediction. So basically the landing, or okay landing, or go around advisory. Okay, all good so far? Yes, one thing I didn't say. Please, since it's a tutorial, you can ask questions at any point. So don't wait until the end. Yeah, please. It's no. So each one of these is a floating point number, float number. It's a real number if you want to abstract. But, yeah. I mean, yeah. If you want the whole thing there, the input layer is a vector of 6 numbers, but I split them into different inputs just to, different variables so that we have one variable per one value per variable. Okay, so we can do, well, once we have this model of the behavior of the program, we can do formalized safety verification as usual. In particular, we're going to look at extensional properties, so a specification on the input and a specification on the output. So any execution that satisfies the input specification should satisfy the output specification. So we have the obvious usual case. We want a program to be safe if all its executions are safe to satisfy the specification. And this allows us to do an abstraction and prove the safety on the abstraction and directly imply the safety of the original model. So this is very standard. It's what we do all the time. Okay. I just want to do this because I want to introduce some abstract domains that we will use later, so you know how they work. Okay, so as an example, for instance, on our model, we can have a specification that puts the range of values for these inputs between -1 and 1. So we can normalize all of them between -1 and 1. And with this, with all these values normalized, what we are saying is that what we get is always a go-around output. So, a landing output. So in essence, when the ranges are between -1 and 1, the braking distance estimation is always smaller than the length of the runway. So it's always safe to land. Okay. So if we want to verify this, we can use this using, normal abstract domains, right? So in the typical recipe steps, 3 steps recipe that we need to develop a static analysis, we can go directly to the abstract domains. I don't think I need to tell you about the concrete semantics. For the hyperproperties, I will do all the 3 steps. But for now, we can just skip to the domains. So obviously, we're going to start with an abstraction of the input. We're going to then propagate this abstraction forward, doing an abstraction of all the computations until we get an abstraction of the output. And then we have to check if the output is included in the expected output. If so, we are safe, and otherwise we have an alarm because we are doing over approximations. So we may have over approximated too much, and we could also have cases in which the model satisfies the property, but we cannot prove it with the abstraction. Or maybe the model doesn't satisfy the property, but we don't know. Okay, so obviously, the first trivial thing to do is use the interval domain. So we can basically associate an interval range, numerical range, to all nodes in the network and see if we can prove the property with this. So our input specification will be assigning the interval -1, 1 to all input variables. And the output specification will be, I'm making it like this because it's slightly more precise than checking with the interval ranges. So I'm basically checking if the x50 is always greater than x51, or whether the difference is always positive, basically. It's slightly more precise if I do this because I have one extra operation that may allow me to do more precise things. Okay, if I do that, then I'm splitting the ReLU into 2 steps. So basically I do the affine transformation first. This gives me this range. I did the computations with a tool, so they should be okay. So the range is -2, 6. So when I apply the ReLU function, the -2 will be reset to 0, and the upper bound remains the same. I can do the same for, of course, the other values in the first layer. So for x11, I get 0 and 3 something as an upper bound. For x12 is 0, 5 something as an upper bound, and so on. I can do the rest of the computations. This is very standard, it's intervals, right? Until the end. At the end, what I get, you see it's a very large bounds for this difference between the output, and we obviously cannot prove the property with this. So the lower bound, we want to prove that it's 0, but here we get -6,000. So obviously we need to be a bit more precise. In the literature, there have been proposals for several domains that improve this, of course. I wanted to present a couple of them, and then a reduced product of them. And then I'll give you some pointers to what we can do better, what is the state of the art in the space. But as a simple examples for a tutorial, I think the other domains are better to at least get the idea of how things work. Okay, so one thing we can do a bit better is to use a symbolic expressions. The problem with the ReLUs here is basically the moment we have with intervals at least, we just have numerical ranges, so we have no idea of whether some variables can cancel out with each other, so we have no relations between variables, and so this becomes very imprecise. So the idea of this domain is to try to have some relations that hopefully cancel out and improve the precision of the abstraction. So what the idea is that we're going to have, in addition to the regular bounds, numerical bounds for a node, we're going to have an expression as well. And the expression should represent the value of the node symbolically in terms of the input variables, plus some other variables that appear in the rest of the program. I'll show you how this works. So, for instance, as an input here, well, the input variables, the expression that represents them is just the input variable. So for x00 is going to be x00 and so on. The range is -1, 1, as usual. Now we have this one, this affine transformation here. The expressions are the ones that we have here. So what this thing is saying is basically if you have an assignment, an affine transformation, so a normal assignment like this, we basically can just plug in, instead of the variable, we can plug in the expression, and this gives us the new expression that we can plug in there. Here, it's very simple. The expressions are just the variables, so it's really the same thing, at least at this layer. So the interval range computation that we get is the same as before with the boxes. In some cases, then you see that going forward in the computations, you can get actually better results. Just because the expressions because this expression will be propagated further, and then you can maybe you have some x2 variable that cancels out with some other operation that you do later on, so you shrink the bounds like this. With the ReLU, basically what happens is you have different cases depending on the values of the bounds. So if you know that everything is positive, so the lower bound is positive or equal to 0, it's the identity function, so the linear expression remains the same. If it's negative, everything is set to 0, including the expression. The in-between case is where you introduce essentially a new expression, and this new expression is the one that will be propagated forward and will be used to represent that particular node later on in other symbolic expressions. In this particular case, we are in the middle case here, where the lower bound is negative and the upper bound is positive. So yeah, we are unlucky in the sense that we have to already introduce a new expression, so we don't gain anything compared to the interval domain. I'll show you later on. I mean, in this particular case, it doesn't quite work, but later on we do better with this domain than just boxes. Yeah, the same happens for the other ReLUs, right? We are unlucky because they're all introduce new expressions, and here, for instance, you see that x41, no, well, this one is actually is not the good case. Where is, no, yes, this is the good case, but I did it wrong. Well, okay, I mean, it doesn't matter. Okay, I could have simplified it further because x41 has a bound that is 0, 0, so I could have used the 0 case instead of the identity function, but yeah. Sorry, I can fix this. But in any case, the end result, what we get, is that the difference now depends on basically x40 and x42, because this one is 0, even though I wrote this whole mess here, but the bounds are 0. So we have that the difference here now depends on these two expressions. And these two expressions have these bounds here, so 0, 1000 something, 0, 191. And the bounds that we get are the same as the intervals. So we are a bit unlucky in this case, and the problem comes already from this layer here. Because with the ReLU abstraction, at this point, we're basically losing all the relationship with the input layer. So we don't gain anything in this particular case. So what people have proposed is another abstract domain, which is this deep poly abstract domain that tries to maintain some relationship with the inputs, also in case of a ReLU abstraction that is undetermined like that. So here, instead of a single expression, so we still have the concrete lower and upper bounds, but now instead of a single expression, we have a symbolic lower and upper bounds. So the beginning is very similar. At the first layer is also very similar. We just have to do well, actually, not quite. Actually, in deep poly, we store the lower and upper bounds. What changes is how the concrete bounds are computed using the symbolic bounds. But at the first layer, things nothing really changes. We still have the same lower and upper bounds, so now it's duplicated. So the interval range is the same. What matters is what we do with the ReLU. With the ReLU, in fact, aside from the trivial cases where everything is active or everything is inactive, in the intermediate cases when the lower bound is negative and the upper bound is positive, we have two cases. What they basically want to do is still have an upper bound and a lower bound on the ReLU. But that still depends on the variables in the previous layer or indirectly on the input. So for instance, here, the ReLU is on the result of this affine transformation x10 prime. What we want is then obtain an upper bound that depends on x0 prime and a lower bound that may also depend on x0 prime or is 0. The choice is between the upper bound is the same. So basically, the ReLU function is this. So it's 0 when it's negative, and the identity function when it's positive. The upper bound, so it's basically this this line here. And for the lower bound, we have a choice between this one. This, if you look at this triangle, it's basically the best convex approximation of the function. So the lower bound, you have two choices: either this edge or this edge. of this triangle approximation. So either you pick the 0 or you pick this x lower bound. And the choice between them is basically given, or at least in the domain definition, the choice is made by the one that reduces as much as possible the extra approximation that is introduced. So it makes this area or this area smaller. And so these are the conditions, basically. So when it's roughly balanced, the bounds are roughly balanced around 0, then this abstraction is preferred. So the lower bound 0 is preferred. And otherwise, this one is preferred with a lower bound x. So in this particular case, we are, I don't remember which case it is, but I think it's this one here. And so what the expression that we get is this one. So it's, and you see it depends on x prime, which in turn depends on the inputs. So we still have some relationship with the inputs, which we didn't have with the previous abstraction. Nonetheless, when you then continue, I'll spare you the rest of the computations because it becomes a bit boring in the end. When you when you actually do the rest of the computation, you get a worse upper bound than before. So this was actually, for comparison, this was the result that we got before. So we get a better lower bound, actually. So we get a minus 1,000, which is still not enough to prove that it's greater than 0, but a worse upper bound there. We got a 5,000 before, and now we get a 9,000. So it's really much worse in terms of the upper bound. So what suggests this is that in practice, neither of these domains is better than the other. So some work that my PhD student Dennis did was to do a reduced product of this. So essentially, every time we do an operation, we communicate the bounds that we computed, and then we can refine the bounds that we are using during the abstraction. Okay, so with that, in this particular case, with this reduced product, so we do this symbolic domain and this dipoly domain together. What we get is this bounds here. So the upper bound is 5,000, the lower bound is 670. And this allows us to prove that we are always returning a okay, we can land result. Okay, as I said, this is not the state of the art, of course. This is a way to improve. The state of the art actually is this. This is what is used, what wins the neural network competition. So there's an optimized version of the ReLU approximation, where the lower bound is basically optimized to reduce the bounds. And this abstraction is coupled with a branching heuristics. And this actually is very effective in practice for this kind of problems. So you can do a better safety analysis with this thing, of course. But for the purpose of the tutorial, what we have seen so far is enough. There is also a line of work that goes into the, as you have seen, we do this abstraction of the ReLUs one by one. So each ReLU node is abstracted in isolation. You can do better if you do abstractions that consider multiple neurons. So here, a single neuron approximation will give you this result, while a multi-neuron approximation will give you a much better convex hull. So there is a line of research that goes also in this direction to improve precision. Okay, this was for safety. Now for the rest of the time, I want to talk about hyperproperties. So in particular, one thing that when I got this problem, I was tasked to do was to basically prove that in some conditions, if I just, so let's say I measure this breaking distance estimation at a certain altitude, like I have an expectation for when I should measure the breaking distance. If I slightly modify this altitude, but no other parameters, the advisory that I obtain should not change. So in particular, I'm not saying anything about what is the advisory that I'm expecting. I'm saying if I'm expecting a landing advisory and I vary only the altitude, then it should remain a landing advisory. But if the advisories go around, the same. If I just vary the altitude, I want to still go around the expectation. So it's not a safety property. It's really saying, well, whatever the result is, this result should not change if I just vary the altitude. So basically, well, since Roberto is the chair, I decided that it was fun to formalize this property as a abstract non-interference kind of thing. So basically what I'm saying is, the property that I'm interested in is considers an input abstraction and some output abstraction. And I'm saying if the input abstraction between two traces is the same, then should also be the same output abstraction of these two traces. And the property is the set of all executions that satisfy this, this property here, which is absolute non-interference. In that case, then we have to use actually, so it's a property not about single executions, so we need sets of executions, so we need to go to the collecting semantics of the program. And so we need to abstract the collecting semantics if you want to consider abstractions, okay? So as an example, then I'll use the altitude example. So for instance, the input abstraction can reset, so it can keep its the identity function for all parameters except for the altitude. The altitude is sort of the value of the altitude is forgotten. We don't care about its value. And the result is, well, basically I'm just mapping x50 and x51 to 1 if I'm returning, so if x50 and x51, x50 is greater than x51, so x50 is the result, the advisory that I obtain, and otherwise it's 0, and vice versa. So I'm basically mapping the result of the classification to 1, 0 or 0, 1. We can ignore the equality case. But, so essentially the risk should not change when I just vary the altitude in the expected range, of course, and nothing else. So how we do this this kind of abstraction? As I said, I want to go through the 3-step recipes, just because it's more fun, more interesting. So first of all, the concrete semantics. As I said, we need to start with the collecting semantics. This is a property of sets of executions. But of course, this has too much information. We don't really need all this information to prove this property. So we can throw away some information and still be sound and complete for reasoning about this property. In particular, if you remember, the property is about input abstraction and output abstraction. So anything that is in between, we don't care. So we can abstract these executions into dependencies between the inputs and the outputs. And then there is another observation that is, so this is obvious. There is something more interesting that we can do is really this is about the abstractions. And in particular, we want to reason about abstractions that have the same, executions that have the same output abstraction and abstraction that have the same input abstraction. So this basically suggests us that we can do this reasoning in parallel, independently, for different input and output abstractions. So essentially, we can partition our sets of executions into different partitions and do all the reasoning in parallel between different output abstractions, different input abstractions, and so on. I'm just going a bit fast in this, but I really just wanted to give you the intuition on how we get to the end result, basically. But it all comes from observing what this property is and how we can leverage the definition of the property to basically simplify the analysis afterwards. And when we do this splitting, partitioning, what we actually get is, in essence, especially when we partition with respect to the same output, if you look at this property here, you can also invert the implication, of course, if you have two abstractions that have different output, sets of executions that have different output, or two executions that have different output abstractions, they should have different input abstractions. So basically, this gives us this lemma. So we have a partition. We can partition the inputs. So this input partitions, we can do a partitioning of the input, and then we can take any two sets of executions that have a different output abstractions, and then we want that their corresponding input abstractions should also not have an intersection. I'll show this with an example, basically. This x2 is our altitude, right? We have two cases. In here, we have essentially I'm projecting into dimensions for simplicity, but let's say we have all other values are projected here. Here we have the altitude. In these cases, then we have, it's okay to land. In all these cases, we have to go around. And here, instead, in all these cases, it's okay to land. And in these cases, we have to go around. Now, if we do, so these these executions here and these executions here have a different outcomes. So they have a different output abstraction. Same for these ones. Now we can do the input abstractions, which means, in essence, forgetting about the value of x2. If you do that, you see that here we have an intersection between the two sets, and here we don't. So these sets of executions do not satisfy the property, while these do. So this gives us basically an idea for how we can do the analysis for this property. And of course, we can basically leverage the static forward analysis that I've seen before for safety. But now starting from a partition of the input space. Of course, I'm not saying anything in how I do this partition. No? I will tell you in a moment. But then, yeah, we can partition the input, and then we can proceed forward. We can do it in parallel. We can fully parallelize this. And then we can check. We can do two things. So if we get in a partition a unique classification outcome, there is no way that we can change the result there. If we had done the partition properly, of course. So these are automatically safe for the hyper property, so we don't need to consider them. And then in the other case, we consider, we collect the abstract activation patterns, and I'll show you why. So in the example, for instance, we start with this input. So here, basically, it's almost the entire input space, except that I reduced x3 to be between -1 and 0. In this case here, what we get is that x50 is 1 and x51 is 0. I'm using the poly in this, oh, no, the product even. Okay, yeah. Okay, this one, I get a unique classification, which is okay to land. So this is automatically safe. In this partition here, I don't get this. So we don't know what is the outcome. It could be 1 in one case, 1 in the other. So what I collect is also what I could collect is basically the ranges of the variables or the abstraction of the variables and so on. But what is more interesting to collect is also the activation status of the ReLUs. So when I say 1, it means that this is always active. When I say 0, is always inactive. So it's reset to 0. And when it's a question mark, is this undetermined case. So it's lower bound is negative, the upper bound is positive. So in this case here, I have two undetermined nodes. With this other partition, what I changed, I don't remember. Yeah, I changed x1. So I changed x1 between -1 and 0 and 0, 1. Here, I also get an undetermined case, and so on. But what is interesting is here, for instance, we have two partitions. But if you look, they have the same, what I call abstract activation pattern. And in fact, it happens very often that several partitions of the input space end up sharing the same activation pattern. So this basically suggests that we can leverage these patterns to actually do the backward analysis with less information. So for instance here, yeah, we can basically do the backward analysis for each activation pattern. So we're going to have an abstraction for each classification outcome because we want the output abstractions to be different. We're going to do the analysis backward for each activation pattern. And then we can leverage this result to intersect with the corresponding partitions where this matters and check for this disjointness or not when we do the input abstraction. To be more concrete, I'll show you in the example. We have these two partitions. They share the same pattern, so this is the one that we will leverage. We're going to start with the abstraction that says that we always return a landing result, or we always return a go-around result. Now we have to analyze this output layer here. So the pattern here is this one. We know that x40 is always active. x41 is always inactive. x42 is undetermined. So yeah, sorry. We first have to do, substitute x50 and x51 with the corresponding affine transformations, of course. This is what we get. We get some expression, some constraint. And then we consider this layer. Of course, we would have, if we want to be super precise, we can consider all possible paths, right? So these are all possible cases. x40 is inactive, active, and so on, all combinations. With this pattern, if we do the backward analysis with this, we can do it normally with joints and so on, and we'll be very imprecise. If we want to do with this joint polyhedra, it's going to be very costly. With this pattern, we can throw away some paths. So for instance, if we know that 1 is always active, we can completely ignore this part of the branches. X41 is always inactive, so we can ignore this other path. So what we end up with is, if we want to do the disjoint polyhedra thing, we can consider just these 2 cases, or well, 4 cases, or 2 cases for each outcome. If we do that, then we end up with these 4 cases. We can keep going. Here, everything is fixed, everything is active, so we only have 1 straight line path to analyze. And here now we have again another undetermined case, so we multiply by 2, so we get 8 possible inputs or input partitions that can lead to different outcomes. And now we have to do this, this intersection checking and so on. So basically we take any 2 polyhedra that lead to different outcomes and check if we do the input abstraction on them, if there is an intersection or not. In this case, if we do it, it's all fine. So we have no intersection. So from this partition, even if we cannot determine with this forward analysis that we always obtain the same outcome, we can obtain different outcomes, but they're all safe because they don't depend on the altitude value, basically. And this one, we have actually intersection. And if we look inside the intersection, we actually can find the counterexample or a set of counterexamples, but this is one, for instance. So in particular, in this case is here, if we fix x0 to be 1, x01 to be 1, x03 to be 1, x04 to be 1, and x05 to be -1, and we just change the value of -2, x02 between -1 and 1, then we get different results. With this, with x02 and -1, we get a landing advisory. With x02 and 1, we get a go-around advisory. So with this kind of analysis, if we do this joint polyhedra thing, we actually also get counterexamples. Of course, it's not complete. In some cases, we have to give up because it's the analysis will be too expensive to do. I'll show you how, in particular when we think about the implementation. So what I didn't tell you is how we do the partitioning. Of course, we can do it in various ways. We can find a partition up front, or we can do it iteratively. So one thing that worked, at least in this case, was to do it iteratively. But then, of course, like based on which criteria. And since we leverage these activation patterns in the backward analysis, one good criteria for deciding if we need to partition or not is deciding, basically fixing an upper bound on the number of undetermined nodes in an activation pattern. So basically you say, I want my abstract activation pattern to have at most u ReLUs that are undetermined. If it's the activation pattern that I get from this partition doesn't satisfy this upper bound, then I split the partition. And then, of course, you want the analysis to terminate. So you put a lower bound also on the size of the partition. So at that point, you become not complete, of course, because at some point, you will hit a lower bound, for instance. So then on that partition that you cannot split anymore, but still doesn't satisfy your upper bound, you have to say that you don't know if the property is true or not. But the good case is when you can conclude, you can also find counterexamples. And then is, well, okay, we split the partition, but in how and in which dimension, along which dimension and how we split. And there are different ways that you can do this, the partitioning. So the trivial naive one, this was an example using deep poly, is, well, you pick one dimension randomly, or you pick, actually, no, what we can do, yeah, you look at the ranges of the inputs, and then among those that have the largest range, you pick one dimension randomly, and you keep splitting. So what we get here with an analysis like this, when I put the check mark here, are the partitions that are considered directly safe because we obtain one classification outcomes. All the others are partitions that need to be analyzed with a backward analysis. So it's like this, it's quite large. In fact, we can do better because with this abstraction, especially with the deep poly abstraction, we have as I said, we have these linear relations or linear expressions that try to maintain some relation with the inputs. So we can actually leverage these expressions to make a better choice in the partitioning. So this was work done by my other PhD student, Serge. So what he did was basically look at the expressions that we obtain in output and look at the coefficients of these output variables. And the ones that have a larger coefficients, they basically have directly a larger impact on the result. And so picking the variables that have a larger coefficients in these expressions is a better choice for the partitioning. So here, for instance, x5 has the largest coefficient. So if you split x5 first, you see the tree is much, much smaller. So we end up with only 4 partitions that we have to handle with the backward analysis. Of course, there is an interesting other bit of information that not all domains that we use in the neural network verification are actually guaranteed that you get a better result when you do the input refinement. For instance, for the poly here, in this particular case, if you look at the bounds that you get, in particular between, well, this one and this one, the bounds that you get here after splitting, so you have a much smaller input space, but you get worse bounds than what you had before. Both the lower and upper bound are worse. And they're even worse than this one up here. So with 2 more reductions of the inputs, we still get worse bounds in the output. And it's even worse when we do the other partitioning strategy with the input range. At some point, with a much smaller partition in input, we get worse bounds than with the larger input partition. So it's using the poly with input partitioning doesn't guarantee that you do better. So you need to use domains that guarantee an improvement with an input partition. Like the product domain is fine. The alpha beta crown abstraction that I mentioned earlier is not stable either. But in practice, because of their bounding strategy, it kind of works. But there are no theoretical guarantees that you always improve when you split. Okay, and then finally, I put I put this lower and upper bounds. But of course, how do you choose this lower and upper bounds? It depends on what you want to do. So I show some, this on the toy example. So of course, the times are not that, the time difference is not that big. So what I did, I put different choices of lower and upper bounds. So in the network there, I don't remember how many ReLUs we can have, but yeah, I put an upper bound of 6 or 2, and the size of the partition is 2, the largest, and I put 1 and 0.5 as the minimum. And I tried different domains and different partitioning strategies, and I show you a bit of like how much of the input space we can analyze and how much time it takes. So you see that with the same input configuration, let's look here, for instance, 0.5 and 2. Of course, with the better domains, you get better results. And in some cases, actually, yeah, maybe this is interesting. Here, I mean, you have seen that the symbolic domains is a bit more expensive than intervals. So as a result, you are more precise, but you can actually also be a bit faster in some cases. So here, we get worse results with intervals. And we get with the symbolic domain, we get better results in a smaller time. This is because of how the analysis is set up. With a more precise domain, you can actually gain a lot of time in the rest of the analysis, because with a worse analysis, you end up with a very costly backward analysis. While if you slightly improve, you do more effort in the forward analysis, you can improve a lot, or you do much less in the backward analysis and gain a lot of time. In particular, the product domain is typically the one that is the most precise, and it takes, well, typically less time. Of course, I did not try with the state-of-the-art strategy. I mean, I did not need it for this particular project. But of course, for larger networks, we need to go have better forward analysis, of course. Okay, so this is, well, basically in terms of the tutorial, this is all I wanted to show you. It's a bit of a summary of what we have seen. I hope it was okay. As I said, if you want to see more perspective kind of things, so what we can do in the neural network verification or formal methods for machine learning in general, you have to come to NSA on Tuesday. Thanks.
Okay, thank you, Katerina, for the great talk. Questions? Okay.
Hi, excellent talk. So I was just curious to know about your experience with, how these tools are integrated into the workflow, because it seems like you have an actual use case where they are being used. So.
I don't know how to operate it. Oh, okay, it's on. Okay, so in this particular case, so they have this need to verify this surrogate models. So what I proposed was just a prototype that showed how this analysis was possible and how it could prove the property that they wanted. Then I don't think they used my code integrated. I think they re-implemented potentially the thing in there. Yeah, so in this case, it worked like that. But I don't know if I can say. Not that big. No, I think on the ACAS XU scale, roughly. Yeah.
So input splitting can be very notorious when the number of dimensions increase. So, I mean, I'm sure this works on smaller Casu networks, but what happens when the networks increase and the number of input dimensions increase?
Yeah, it's mainly about the input dimension that it's more. It impacts more the scalability of the thing, the input dimension, and also the input, the property that you want on the input. So we can do very large networks on this robustness properties on images, but of course the robustness properties are local and very small. So yeah, this allows us to scale, but it doesn't say much about the rest of the input space. So in this particular case, it was fine because the model was rather contained. The input space was actually small, so it was fine. We could also do very complicated analysis like this, or very complicated, analysis like this. But yeah, if you want something larger with complicated properties, yeah, you need more. You certainly need to parallelize. So we didn't need to parallelize on GPUs, for instance, or anything like that. If you want probably on a very more large scale thing, yeah, you definitely need to use state-of-the-art analysis, parallelize over GPUs and so on. So yeah, you need more. And you cannot scale to very large things, at least for sophisticated properties like that. No. Yep.
Mm-hmm. I have not understood why your partitioning is always boxes and not some other structure.
Yeah.
And the second one is because you compute with floats, do your abstraction or are your abstraction sound for float computation?
So the partitioning with boxes is because it's easier. It would be better to partition differently. But it's not easy to then use the simpler abstractions that start with the boxes input. And for the floating points, so in this particular case, the implementation I use is not actually sound. That's also why they didn't use my code probably. But you can use abstractions like deep poly and so on that are, you can implement them to be sound with respect to the floating point underlying semantics. So the prototype doesn't do any of that, but you can. There.
I'm a little bit curious about how would you do the input-output abstraction in general ways, like
can be anything. Huh?
And just following up the question before earlier, that when the input concerns about multidimensionals, and then would that be changed in a way that, well, how would you know what kind of abstraction or input specification? I think most of the case, that's like we don't really know if we want to ensure that all the transformation are correct, right?
Yeah, so I mean, the formalization was very general. You can have some abstraction of the input, some abstraction of the output, and you want to prove this property. You can, in the particular use case that I had, it was very straightforward to define what the input abstraction is and what the output abstraction is. I just found nice to use this formalism because Roberto is an author of that. But in practice, I think it depends on the context, right? On the property that you actually want to verify. Then you can define it.
I see. Thanks.
Yeah.
So the inputs look like they kind of are using like L infinity norm because intervals. So if you want to prove properties on L2 norm or L1 norm, like how the abstraction change or if the system would work.
Okay, I'm not proving robustness. So the ranges I have is really the expected ranges for those inputs. So I'm not proving any robustness or I don't have any local point and a ball around this point. If your input abstraction should take into account the distances between points in the hyperproperty case, then you need to have some representation that is allowed to that allows you to reason about these different notions of distance. In this case, there was nothing of that. It was in that case. That abstraction is actually similar to the cell infinity in principle. I think. It depends on the property, and you need to then define an input abstraction that accommodates that.
Do you need to change the abstractions you're using in that case?
I don't think so. No, just the abstraction that you use. I think. Yeah, Patrick is another one.
I don't remember exactly ReLU, but if I remember well, there is a test inside.
The ReLU.
Yes.
It's basically a max between the linear expression and 0.
And so, but you could kind of the test you could kind of propagate it, no?
I don't know. What do you mean?
Like a conditional in a program that is.
Oh, you mean do some sort of partitioning?
Yes.
Yes, but you have many of them, and then it becomes very, very expensive.
Okay. Okay. So, stupid question.
No, it's fine. It's fine. Okay.
Any other questions? So let's thank Katerina again.
Thank you.
So our next talk will be about robustness verification of multi-label neural network classifiers. The presentation will be made by Julian Moore from Technion Institute of Technology in Israel. So when you're ready, you can start.
Okay, so hi everyone, I'm Julian. In this talk I'm going to talk about my work about robustness verification of multi-label neural network classifiers. So to begin with, I'll introduce a bit of background. So what is a multi-label neural network? Given an input, in this case an image, we pass it to a multi-label neural network, and we get a set of scores and a set of labels. In this case, we have a 4-label neural network. So the neural network classifies this input to the top 4 labels, the 4 labels with the maximal scores. So in the multi-label scenario, we have an input, and it's assigned to a set of labels. Multi-label neural networks are used in many useful and important applications, such as image annotation, object detection, automated facial action unit detection, and many more. And I want to address the main problem on this work, which is adversarial attacks. So what is an adversarial attack? Given an input, the original input we saw, we add a very small perturbation, a very small error to the input that we as human, we cannot see. We see the same image. But when we pass the perturbed input to the same neural network, we get a misclassification. So for this perturbed input, we get that we have a boat in the perturbed input. We obviously don't have a boat instead of a bus. So the score of a boat is greater than the score of a bus. Our goal is to analyze the local robustness of a multi-label image classifier in a given input neighborhood. Or in other words, we want to see how reliable is a multi-label classifier for a set of inputs. Now for more formal definitions, I want to define the definition local robustness, specifically multi-label local robustness, but we'll first start with single label local robustness. So what's local robustness for single label neural networks? Given a single label neural network, an image, and a classified single label, I want to look at the neighborhood of the image. What's the neighborhood? It's a set of inputs. We'll define it more formally later, but for now, it's a set of inputs around the original image. Local robustness in single label neural networks require that all the inputs in the neighborhoods would be classified to the same predicted input as the original image, meaning all inputs in the neighborhood, all inputs in this set would be classified to the label cat. Passing to the multi-label scenario, we want to adapt this definition of the single label neural networks and try to put it here. So similarly, we would say that the input, looking at a neighborhood around it, we want the same set of labels to be classified to each input in the neighborhood. This is a possible definition for the multi-label scenario, but it can be too strict. An alternative, we can only choose only an important subset of labels that we want to preserve as predicted or not predicted in the neighborhood. Meaning for this case, I only care about the label person and the label car and the label horse. I want all inputs in the neighborhood to be always classified to these two labels, the person and the car, but never classified to a horse. So we choose a subset of labels that we care about, and we define the local robustness accordingly. A formal definition, we want to define two sets of labels, disjoint set of labels. We call L in and L out, and an input, and given an input neighborhood, our classified is called locally robust if for all inputs in the neighborhood, each label in L in is a predicted label, and each label in L out is never a predicted label in the neighborhood. Meaning we want to preserve all labels in L in as classified and all labels in L out as unclassified. The rest of the labels we denote as the set L may. These labels that can be in either predicted or not predicted in the neighborhood. A quick example. So I want to define L in as the set of labels 1 and 7, and the set L out as the set of labels 2, 3, 4, 5, and 6. Given this, x prime is a sample in the neighborhood. So we have the original image x, which is classified to 1 and 7, and x prime, an input in the neighborhood that it's classified to 1 and 8. Obviously, we can see that if we choose 7 to be in Ln, then the neural network for this definition would not be robust, because 7 is not predicted in an input in the neighborhood. In a similar way,
it could be on the 10th decimal, the difference could be very small.
Yes, right, between the scores.
Yeah, so it must be exactly can be very close. So
right, but the neural network itself classify the same image. It chooses just two maximal scores, in this case 1 and 8, even though there's a very small, well, this is the definition of an adversarial attack at the end. We can have very little error in the scores and in the image, and to classify this adversarial attack to wrong classes. In this case, the 8 instead of the 7. In a similar way, we have the 8 here in the set of L out. Also, the neural network will not be robust for the same reasons. And here comes our goal. Our goal is to find the maximal set L in and L out for which the neural network would be robust. Okay, so now I want to define more what's an input neighborhood more formally. In our paper, we focused on epsilon balls with respect to the L infinity norm. What's an epsilon ball? In simpler words, I'd say that given the original image, I can add or subtract at most a value of epsilon to all pixels, and I'd stay in the epsilon ball neighborhood. So we defined what's local robustness for multi-label neural networks and what's a neighborhood. And now we want to compute the maximal L in and L out sets for a given neural network, an image, and a neighborhood. Our main challenge was that the property requires reasoning for all labels to be classified to either L in, L out, or L may. Therefore, the complexity of an exact analysis can be potentially increased. We present our multi-label local robustness certifier called malloc. Malloc relies on fast and optimistic queries in the form of sampling, numerical optimization, and fast mixed integer programs, and fast linear programs. And for the remaining unclassified labels, it runs an exact sound and complete MIP analysis. So now what I'm going to do, I'm going to explain about each of the three components: the sampling, the pairwise relation analysis, and the exact MIP analysis. But before that, we have a pre-processing step. What's the pre-processing step? We just take the original image, pass it through the neural network, we get the scores of the labels, and we rank the labels according to the scores. And then we have in front of us the predicted labels. An additional step that I want to do, I want to save the candidates for the L-in set and for the L-out set. The candidates for the L-in set would be the predicted labels of the original image, I denoted as S-in. And for L-out would be the rest of the candidates, the rest of the labels, which I denote by S-out. Okay, let's start with the first component, sampling. So basically, what we do in sample, we want to sample counterexamples to labels in S-in or S-out from the neighborhood. What mallocs do actually when finding a counterexample, it removes from S-in or S-out the candidate labels. It removes them from S-in or S-out and put them in L-may if a counterexample is found. So let's look at an example. Given the candidates, the initial candidates and the neighborhood, we sample an input from this neighborhood, X prime, we pass it to the neural network and get our predicted labels. In this case, we can see that the predicted labels are 9, 3, and 8. So we can see that 0 is an unpredicted label for X prime, which can I say that it can never be in L-in, since I found a counterexample. In a similar way, I can say the same thing about 8. It's originally an unpredicted label, but in this case, I found a counterexample for which it is a predicted label. And I can say that it can never be in L-out. So I take both 0 and 8 from the candidates, and I can add them to the set L-may. You may ask, how do we sample? So we have two techniques. First, uniform sampling. We just randomly sample uniformly from the neighborhood. Or corner sampling. What corner sampling does is that it uniforms, it samples uniformly from the corners of the neighborhood samples. What's the corners of the neighborhood? It either gives each pixel a perturbation of epsilon or minus epsilon, and nothing in between. What's the motivation behind that? The further we get from the original image, we expect the scores of the labels to differ more. So this was the first component, a simple component, and the first component tried to classify labels into the LMA set mainly, to find counterexamples and classify labels to the LMA set. Now we have the pairwise relation analysis. This component's goal is to examine every label L1 and L2 relation. So we look at pair of labels L1 and L2 where L1 is a predicted label and L2 is an unpredicted label. And we want to check how strong is their relation in the neighborhood. So what does that mean? A strong relation would say that the score of L1 is always greater than the score of L2 in the whole neighborhood, for all inputs in the neighborhood. So they preserve this relation in the whole neighborhood. A weak relation can say that we can achieve a swap between the label L1 and the label L2, meaning I can find a counterexample in the neighborhood for which L1 is an unpredicted label, and instead L2 would be a predicted label. So we define the numerical optimization swap attacks. This is the first part. And like sampling, it also searches for counterexamples in the neighborhood, but it does that with a guided search, where we have a target and we want to perform a guided search in the neighborhood to find a counterexample. So as I said before, our target is to swap between L1 and L2, to take L1 out of the predicted labels and instead of it to put L2. For this we used we rely on the given multi-label targeted adversarial attack called TKML adversarial perturbations. What does that attack do is we give it a neural network, an original input and an epsilon. And we also give it a desired K predicted labels, a set of labels. And using gradient descent, this attack would tries to find us a counterexample. And if it succeeds, the counterexample predicted labels would be similar to the desired K predicted labels we passed. So to transform the TKML attack to our swap attack, we would only need to define the desired K predicted labels. And to achieve a swap, we would take excess predicted labels, remove L1, and instead we would add L2. For example, we use this attack, and we want to try a swap between the labels 0 and 1. So we define the desired predicted labels as 1, 3, and 9. We removed 0 from the predicted labels, and instead we put 1. In this case, the attack succeeds, and we get a counterexample as wanted. Like before in sampling, we can then remove some candidates from SIN or S out and put them to LMA. Okay, so the swap attacks, this part, found weak relations. Now I want to try and prove a strong relation. I want to try and prove for a pair of labels L1 and L2 that the score of L1 is always greater than the score of L2 in the neighborhood. How do I do that? We do that using linear programming, mixed integer linear programming, and we need to encode a program to try and prove this property. Okay, so quickly I'll just pass on the encoding. We have our variables, the inputs pixels variables, which represent a sampled pixels values. We got our neural network variables, which represent the neural network's neurons. Regarding the constraints, we need the constraints which represent the epsilon ball neighborhood, or neighborhood that we're looking at, and the constraints which represent the neural network functionality. In addition, the most important constraint is our property constraint. So to remind you that our property would want to check if the score of L1 is always greater than the score of L2. But instead, as a constraint, we would put the opposite. Why we would do that? Because if we pass this program to a solver and we found a solution, meaning the program would be feasible, then we found a counterexample to the relation property, meaning the property does not hold. Otherwise, if the solver says that this program is infeasible, this means there's no sample in the neighborhood that this constraint holds. Right.
Which is always true if B epsilon of x is not empty, and then there is no more x prime afterwards.
Right, so this should be x prime, and x prime L1 and x prime.
One should be x prime, no?
This and this. This one, and x prime L1 and x prime L2. So we found a counterexample in the neighborhood for which the score of L1 sorry. Okay, so this is wrong. We found x prime in the neighborhood for which this property holds, meaning the score of x prime L1 is smaller or equal to the score of the label L2. So this needs fix. Okay. This is not. Okay, so if it's infeasible, meaning we did not find this one, we did not find a counterexample that for which this property holds, meaning our property does hold. And therefore, we can prove a strong relation if we got an infeasible program. Now I want to combine between the swap attacks and the swap MILPs in this kind of way. We initialize two queues, the attack queue and the MILP queue, and we put all the relevant pairs to the attack queue. And then concurrently we perform swap attacks. If an attack works, meaning I found a counterexample and proved a weak relation, then I can use this counterexample and classify some labels to the set LMA. If not, I want to check for this pair of label if it has a strong relation. So I add it to the MILP queue, and one by one I pass it to the MILP worker. And the MILP worker performs swap MILPs and checks whether this pair has a strong relation. For proven strong relations, we want to save these constraints, the strong constraints, in a set of constraints, which we will use now. Looking at these constraints, we want to analyze them. For an L1 label, in this case 3, the label 3, if it has at least C minus K different constraints, where C is the number of all labels and K is the number of predicted labels, this means its score is always larger than C minus K different labels in the neighborhood, which means it is always a predicted label. So we can take this label and add it to LN. And notice that this is the first time we classify labels to LN and not to LMA. In a similar way, regarding the label L2, if it's in K different constraints in this set of constraints, then its score is always less than K different labels in the neighborhood. This means it's always an unpredicted label in the neighborhood, and we can add it to the set of labels L out. The last component, the exact mixed integer program analysis, for which we execute for the remaining unclassified labels. So here we want to take our remaining labels and try to either classify them to the L-in set or the L-out set, and if not succeeded, we would put them in the L-make set. So we define two different properties for two different mixed integer programs. First, we want, okay, so given a set of labels S, we want to try to check, to prove this property, that the whole set of labels S is in Ln. This way, we try to classify a number of labels at once to the set Ln. In a similar way, we will encode the mixed integer program out given the S label, and we try to prove the property that all the labels in S are classified to L out. Okay, so I will show the encoding for the MIP in program, and the MIP out encoding would be very similar, only a little change that I will show later. Okay, how do we encode this program? Okay, we have the same the input and ends variables as before. We also have the neighborhood and ends constraints, also coded as before. This time we have the set of constraints, and we can add it as extra information to the extra knowledge to the program. This will help pruning the source page, and the extra knowledge will definitely help the solver. So we can also add this set of constraints to our program. Okay, so here we start encoding the extra variables that later will help us to form the objective function. First, we want to define a maximum variable. This maximum variable would want to capture the score of the maximum scores of the labels that are not in the set S. To remind you, we are looking at the set S, and we want to check whether S is in Ln. So this maximum variable captures the maximum value of all labels that are not in S. How does that work? We have the v1 variable and a couple of Boolean variables. And their goal is the v1 captures the maximum value, and the Boolean variables captures the maximal label. So the maximal label will have the value 1, and all other Boolean variables will be 0. How do we enforce that? We add these 3 constraints, and we will look at the following case. If a certain label I, we're looking here. If a certain label I is the maximal label, meaning its Boolean variable is true, this constraint enforced v1 to be equal to its score. How does it do that? Because we have this constraint and this constraint, meaning v1 would be equal to the label ith score. Otherwise, the constraints will hold true. You can check that. And that's how we capture the maximum variable. In a similar way, we would want to capture the second maximum variable. So here too, we define v2 and the Boolean variables, and we define the constraints. In this case, we will be looking at the following case. If a certain label I is not the maximal label, but it is the second maximal label, meaning its Boolean variable si1 is 0, and its Boolean variable for the second maximum is true, the constraints will enforce v2 to be equal to its to the ith label score. This case and this case. In this case, v2 would be equal to the label I score. In all other cases, you can check that all constraints would apply. To generalize this, we add this encoding to the jth maximum variable, the third and the fourth and the fifth maximum in the labels that are not in S. In addition to all the previous variables, we want to add a minimum variables, this time on the labels in S. We do that defining similar variables to the maximum and similar constraints to the maximum. Given all of these variables, we define our objective function, which is defined as the following. We want to find the maximum of the difference of the maximum of k minus s plus 1 score minus the vs minimum. In our paper, we proved that given the optimal solution of this objective function, we can say that if the optimal solution is negative, then we prove our property. We prove that S, all labels in S could be classified to Ln. Otherwise, we know that at least one label L in S is not in Ln, meaning it's in Lmay. You can see the proof in our paper, but this proof is mainly based on the definition of the same V, meaning Vk minus S plus 1 being the maximal k minus S plus 1 score of all the labels excluding S. Why does this theorem help us? It helps us to classify the following. So we have, so we say that if we pass S to MIP N, and we have an optimal solution which is negative, we can say that all labels in S could be classified to Ln. So we take all the left candidates, meaning Sn, we pass it as S to MIP N, and if we get a negative solution, our optimistic encoding could classify all labels in Sn at once in Ln. Otherwise, I know that at least one label L in Sn should be classified to Lmay. So we extract this label using the optimal solution we found. We put it in Lmay, remove it from Sn, and we try again. In this way, we check iteratively, and at most, we can classify all labels in Sn with at most Sn iteration, which is limited by k. So as I said, we have also the MIP out encoding, which is similar to the MIP in encoding, except for the objective function, which is this one. But our optimistic encoding is the same, and we use the same method for classifying labels from S out to either L out or Lmay. A little bit of evaluation. We evaluate malloc on 5 different models and 5 different models of different sizes and architectures and 3 different data sets. We evaluated it on different size of label sets, different Ks. This is the label set, different Ks, different epsilons, different sizes of epsilons. From our results, we can see that for small values of epsilons, small neighborhoods, the swap MIPs classify most or all labels to their sets. For larger epsilons, we can see that sampling and swap attacks are more effective, and the exact MIP is finally invoked. We can also see that the more labels classified by these fast queries, the shorter the execution time of the exact MIP as expected, and the exact MIP is the larger component. Also, we can see that the fast queries can give us high percentage of classification within little time, and the fast queries are performed at first in malloc. Lastly, we compare malloc to 2 different variants. The first variant is only the exact MIP with the optimistic encoding. The third variant is only the exact MIP without the optimistic encoding, and we can obviously see that that malloc succeeds to classify a significantly larger percentage of labels under a given time limit. Okay. Lastly, I would like to say that, as we know for now, that malloc is the first local verifier for multi-label classifiers. And that's it. Thank you for listening.
Okay, so you do this sampling at the beginning, and I was wondering, is it useful in any way to do it an over-approximating analysis to at least figure out which labels are definitely not going to be in the output set in any way.
Which first? You mean?
Yeah, I mean, it's on the same level of the sampling, right? To get to know which things are true or not. Yeah. So maybe even earlier, you get at the beginning, yeah, you do this pre-processing thing. Can you also do, as a pre-processing step, a forward analysis from the ball, the epsilon ball that you do, to know which labels are definitely not going to be in the classification set? Maybe?
It is possible. But we can, like, we do have over-approximation in this. Yeah. Like, if you look at the pairwise relation analysis, for an example, we look at the swap between L1 and L2, which is not always, like, we could have very other options, not only a swap. So this can be considered as over-approximation.
Okay.
Not in the way you suggested.
No, it was just maybe to optimize further to.
Yeah.
You don't need to consider, even consider.
Possible, yeah.
I don't know. Just random idea.
Have you tried with larger networks like Cipher10 or like trained on Cipher10 like ResNets and stuff like that?
So for larger networks, when only the last component, you see we have like 3 components here, right? So as the model gets larger and larger, only the exact MIP would be the harder part, like in terms of scalability. So even though we didn't try that, right? But like we have at most we have a big neural network, but not that big in the experiments. But we can say that our fast queries will always perform efficiently, even if the neural network is significantly larger. Because sampling does like, we only sample. Pairwise relation analysis is more related to the number of labels, which it will increase the pairs. So as you increase the model, it will not affect the first and second component, which in a lot of cases do classify the higher percentage of labels. But it will definitely affect the exact analysis.
Okay, thank you.
When you have things like sampling and things like that, optimization, we know that there is something that is erroneous, and so most people they have some probability of being correct or something, and so in the guarantees that when you show us something, it seems to be the truth 100%, but in fact it is not. Because of your sampling, if you sample the border of an image, then and everything in the middle, you will fail completely. So, have you a probabilistic evaluation of the correctness or something like that?
You mean, have I tried like different?
Say, I am correct in 9 out of 10 cases.
Of sampling, like you mean?
Yeah.
For example, okay, so. In sampling, I think like if you want to perform sampling as a simple method, let's say, so like we could use like prior knowledge. Oh, sorry. So we could use prior knowledge to know in which areas we can sample, but we do not do that because we want the sampling component to be fast. Like we want to try random sampling at first, which is the most naive way to do it, the most straightforward way to do it. And then we try a bit harder, like we want to try corner sampling, which it's not proven to be the best, but we suppose like it would be better than random sampling. So in each step of the algorithm, we first start at simpler but more fast methods, which would not guarantee us a big percentage of classification. But as we get further in the algorithm, it gets the analysis gets more exact, but the scalability-wise, it gets larger.
But
so this
your reasoning seems very empirical. That is, do you have some mathematical model that can certify what you say, or Is it just intuition and you say
intuition.
it works because it works?
The sampling meaning, yeah, like we tried on different methods, and at most sampling, yes, we do find counterexamples from a big region of a neighborhood. So it also depends on what neighborhoods you're looking at. Like big neighborhoods, you most likely would find a lot of counterexamples in a couple seconds. Looking at smaller neighborhoods, yeah, sampling would not be that effective. So we move forward to more strict and exact analysis. So it depends where we look, at what's...
and I have another question. If you take a picture which is not focused, it's fuzzy, and so the comparison of the fuzzy picture and the focused picture, does it fit in your B epsilon neighborhood model?
Can you repeat the question?
That is, if you have a notion of a neighborhood, which is a kind of ball around every pixel. If I take a picture by a camera and I don't focus, it becomes fuzzy. Is the fuzzy picture in the neighborhood of the focused picture?
So as I said before, here we looked at a specific type of neighborhoods, which is the epsilon Bohr neighborhoods, but we can easily extend this to other types of neighborhoods. As you said, maybe the blurred family neighborhoods, which we take some images, we blur them at a certain type, and this is a new type of neighborhoods.
Also the deformation of colors, for example.
Yeah, so we have a lot of different neighborhoods. Right.
Okay, thank you.
two talks now. Okay, the first one will be will be given by Philip Kern, right?
Yes, that's right.
Okay. From Karlsruhe Institute of Technology. And the title is Abs Interpretation of Real Neural Networks with Optimizable Polynomial Relaxations. Please.
Okay, then thanks for the introduction. I'm glad I can talk about my work here, which is, of course, a joint work with my supervisor, Carsten Zins. And as you already said, yes, it should work. Okay, which is joint work with my supervisor, Carsten Zins. And of course, it's about verification of Rayleigh neural networks with optimizable polynomial relaxations. Using the talks before, we have already seen why verification of neural networks can be important. Here, for example, when we look at traffic sign recognition in autonomous driving, when we have a sign of a speed limit, we of course want our neural network to always correctly recognize the speed limit sign. And what goes wrong in this case is that some malicious or at least unhelpful man put a tiny sticker in the center of this image, and now it gets classified wrongly in all kinds of ways, as no entry sign, slippery road, or a very high speed limit, and we don't want to have that in practice, of course. Another application would be, for example, in aircraft collision avoidance systems, where we want to see if the other aircraft is close by. We are flying directly towards the other aircraft is flying directly towards us. Then we, of course, don't want to issue a clear of conflict advisory to the pilot, because if we still keep flying straight ahead, we are going to crash into the other airplane. And I want to highlight one thing about these two applications that are going to be important later on, and that is that they are all applications with low input dimensions. So you can see this airborne collision avoidance systems. It has only 5 inputs, like the angles to the other airplane, the distance between the airplanes, and the velocities. And also this the sticker that we placed on the speed limit sign. If we want to verify that our speed limit detection network is robust to stickers placed within some, let's say, 5x5 grid in the center of this the speed limit sign, we only have to treat these 5x5 pixels as variables. And all of the other pixels in the image, they can be set to the exact values that they have in that image. So those are 2 applications where you can get away with looking at very small dimensional input properties. With that out of the way, we're going to have a look at a general problem setting, which is basically just the same as in normal program verification, just that we now have a special program, namely a neural network, and an input property and an output property, and we want to verify that all inputs satisfying the input property. For those, the network's output satisfies the output property. And throughout this talk, we're going to look at our running example, this very small network here. Weights are written above the edges, biases are written next to the nodes, and it uses the ReLU activation function that we've already seen before, which is 0 if its input is less than or equal to 0, and just the identity in all other cases. Now, what is going to be our input property? Throughout the talk, we're going to focus on x, which is in -1 to 1, and we want to prove that the output of this network is always less than or equal to 1/2. Do we even have a chance of proving that? Let's have a quick look at the function this network computes. And as we can see, the maximum output over the domain of interest is 0.4, so we might get lucky in proving our property. And how are we going to prove it? We're not just going to reason about our network directly, because that's a very can be a very complicated function in practice. We're going to use abstraction to construct a valid upper bound u of x on the output of the neural network. And this abstraction is hopefully a lot simpler function that allows us efficient reasoning if this is less than or equal to 1/2. And now for a quick overview over the remainder of the talk. First, we are going to review some background about optimizable linear relaxations. So this u of x will then be a linear function. And then we will see that, oh no, it doesn't suffice to prove our property, and we have to look for other possible relaxations. And this is the contribution of the talk, the main contribution. We're looking at optimizable polynomial relaxations to get a different kind of u of x function. And before we look at the evaluation then, I'm going to quickly talk also about the limitations of our approach. So let's start with the background. This is what Katharina also talked about earlier on, this area optimal relaxation of the Rayleigh activation function. Because Rayleigh is convex, the upper relaxation, you just connect Rayleigh of L to Rayleigh of U. And for the lower relaxation, we have these two choices. If the lower bound is further away from the origin, the area is minimized if we choose the zero function as a lower relaxation. If the upper bound is further away from the origin, then the area is minimized if we take this identity function as a lower bound. And while this is a good heuristic in many cases, it is not always possible to choose to find the best approximation by just looking at this local information of the lower and upper bound to the input of the Rayleigh. And so there are these other approaches that have recognized that you can actually have a lot of different valid lower bounds, namely everything that has a slope between 0 and 1 is a valid lower relaxation of this Rayleigh activation function. And with this parameterization, you can then basically try a lot of different alpha values and then take just the best bound that you get at the output of the neural networks afterwards. Okay, so how is this used in practice? This is used in the back substitution approach. And I'm just going to revisit it here. To calculate these relaxations of the Rayleigh activation function, we've seen that we need these lower and upper bounds on the input of the neural net, of the Rayleigh functions. And we just assume they are given here. And then we proceed with the back substitution. So we are interested in if y is less than or equal to 1/2. What is y? Well, it is just n1 minus n2. We can write that down. We also know what n1 and n2 are. It's just the Rayleigh function applied to the pre-Rayleigh inputs. And then we have to over-approximate these Rayleigh functions somehow. And because we want to have an upper bound on this y, we want to have, we now look at the sign in front of this Rayleigh of n1 hat, and we notice that y is monotonically increasing in Rayleigh of n1 hat. And so if we want to have an upper bound on y, we need to have an upper relaxation of this Rayleigh of n1 hat. We're also going to look at the second Rayleigh term. We realize that y is monotonically decreasing in that term. And if we want to have an upper bound on y, we need to subtract as little as possible to make that as large as possible. And for that, we're going to choose the lower relaxation of this Rayleigh of n2 hat. Let's just, for the first iteration, choose these area minimal relaxations. Write down their expressions, substitute them, and then we can again back substitute through the next linear layer. What is this n1 hat? Well, it's just x1 plus 1/5, the bias. And we can collect the terms, and then we have our simple linear function that we can easily check if it is actually smaller than 1/2 over the domain of interest. Let's quickly check that. And unfortunately, using interval arithmetic, for example, we get that the maximum value is 1.2, which alas is larger than 1/2, and so we have to try something else. And let's first try these optimizable linear or these parameterized linear relaxations with a variable lower bound. So nothing changes here, nothing changes here. We look at the monotonicity pattern again to choose the lower and the upper relaxation. But now we can substitute different bounds for the lower relaxation here. Substitute back again. And now for every choice of alpha for the lower bound, we get a different function that over-approximates the behavior of our neural network. So with alpha equal to 0, we get the original behavior with the area minimal approach. With alpha equals to 2/5, we get a little bit better. With alpha equals to 3/5, we actually get the best possible linear relaxation with this approach right here. But alas, 18/25, so 0.72, that's still larger than 0.5 or 1/2, which we wanted to prove. So we might want to look for a different abstract domain, namely polynomial relaxations. But we not only want to look at static polynomial relaxations, we want to, when we have seen that this optimization approach with the parameterized relaxations, it has quite a large benefit. In the linear case, it brought us from 1.2 as the upper bound to 0.72. And also in practice, I've seen a decrease in the upper bound of oftentimes more than 90%. So we definitely want to keep that and also introduce that into our polynomial relaxations. And that's the main contribution of this paper, parameterized polynomial relaxations for ReLU activation functions. And the question, of course, is what are the parameters that we choose? And the answer is actually quite simple. We're just going to use the monomial coefficients of these polynomials. So we start with any polynomial, any set of monomial coefficients. We can draw this candidate polynomial here. It is, of course, not yet a valid upper relaxation of this ReLU function over the domain of interest. But we can just calculate the maximum difference between the ReLU function and our candidate polynomial and shift it up by that amount. And then it's a valid upper relaxation. And the same can be done for the lower relaxation. We just look at the minimum of this difference. We again start with arbitrary monomial coefficients, calculate this minimum difference, shift it down by that amount, and then we have our valid lower and upper relaxations. And we get this for any value of the monomial coefficients that we choose. So we again have this potential to optimize over these monomial coefficients. And this maximization procedure is actually quite efficient because ReLU is, as you can see, a piecewise linear function. So we only have to solve a univariate polynomial maximization problem, once to the left of the origin and once to the right of the origin. And this is very efficient to do. And now let's see if it is actually better than what we have seen before. Nothing changes here. We again look at the monotonicity pattern, select an upper and a lower relaxation, parameterized by some monomial coefficients. And as an initial guess, we can just take some pre-existing relaxations from the literature, just like these here. But anything else also is okay, because by our process, with any monomial coefficients, we get a valid relaxation. But let's stick with this for the time being. We can back substitute that to the input. We have now a different function u of x that is a polynomial and hopefully easier than the neural network itself, for which we can check if it is less than or equal to 1/2. And in this case, for this function, sadly, it is still 1.2. But keep in mind, we can search via a gradient-based optimization for better monomial coefficients. And if we actually look at these polynomials here, these polynomial relaxations here, when we back substitute, we get this upper relaxation of our neural network behavior. And when we use interval arithmetic to calculate the maximum over the domain of interest, we get 0.453, which is, of course, smaller than 1/2. And now we have proven our property. A quick remark about the efficiency of this approach. I have stated that this maximization itself, to find the valid relaxations, this is just univariate polynomial maximization problems. This is quite cheap. Polynomials can also be represented by matrices of their monomial coefficients. So the propagation through the layers of the network can also be done as matrix multiplications and can be done quite fast. But of course, there is some trade-off where it has to be slower than these linear relaxations. And this is the scalability in the number of unfixed input dimensions. So just because like in the implementation in our paper, we use quadratic polynomials, quadratic relaxations. And of course, linear functions, they have one coefficient per input variable. And quadratic polynomials, they have a quadratic number of coefficients, of monomial coefficients, depending on the input size. And so if we want to scale this up to a very large image properties, the verification time or the time for one pass through the network quickly skyrockets. So this is why I also mentioned in the beginning that there are useful properties in neural network verification where it is sufficient to look at small input dimensionalities. So this is one thing to keep in mind. And the other thing to keep in mind is that while these linear approximations, they work for every layer of the neural network in this back substitution process, the polynomials do not. Because in the linear case, we could just, when you remember during these back substitution slides, we always looked at these ReLU functions and looked at the monotonicity behavior of the output of the network with respect to them. And if it was just to choose if you should choose the lower or the upper relaxation. And in linear functions, you can always look at the leading coefficient of a variable to see if the output is monotonically increasing or decreasing with respect to that variable. And with polynomials, you don't have this anymore. So what we've actually done in our implementation is we used linear relaxations from the end until to the first hidden layer. And then because from the end to the first hidden layer, we have a linear function, we can just look at the sign and see if we should use the lower or the upper relaxation. And then we use the polynomial relaxation just for that first layer and propagate back through that. And this is also a very important limitation of our approach. Okay, but even though I talked about these limitations, we could still see some improvements compared to these optimizable linear relaxations. We actually looked at networks trained on the Cypher 10 image benchmark. Those are 32 by 32 times 3 color channel images. And we evaluated that on 6 by 100 and 9 by 200 layer ReLU networks. And we looked at properties with on the one hand, up to 50 free input dimensions, so basically patches in the center of these images of varying size for one experiment. And for another experiment, we looked at, we kept the number of the unfixed input dimensions fixed, but instead of allowing these unfixed input dimensions to take on arbitrary values in the image domain, we only allowed these dimensions to vary within an epsilon ball of the initial image. And these are the results. So what you see here is the following. Let's take the left graph, for example. On the axis, you see the violation that could be proven by the solvers. Violation is just how far are we from fulfilling the specification. So if you think back to our example at the beginning, we wanted to prove that the neural network's output is smaller than 0.5. And at first, we could only prove that it is smaller than 1.2. So the violation would be 1.2 minus 0.5 is 0.7. And this is what you can see here on the y-axis for our implementation of our solver, which we call polycrown. And on the x-axis for alpha crown, which is the bound propagation backend of the solver alpha beta crown that won the last couple of VNN competitions. And yeah, so far for the axes, let's maybe look at let's maybe look at this data point. Each data point represents a combination of a baseline image with a perturbation, for example, these patches, and a network, so either the 6 by 100 or the 9 by 200 network. And for this particular instance, Polycrown was able to prove a violation of around 10, while AlphaCrown was able to only prove a violation of 1,000. So this is a very large improvement that Polycrown could produce here. And we can see that, although not, of course, very few points lie in this order of magnitude, the general weight is below the diagonal, which means that Polycrown performed better. We can also have a look at this red strip down here, which is the properties where Polycrown achieved a violation of 0, so it was able to prove the properties, while AlphaCrown achieved a larger violation than 0 and so was not able to prove the property. And there are a lot of points where we could prove something that AlphaCrown could not. AlphaCrown could also prove something that we could not, but also way fewer points. And yeah, the same issue, or the same picture is also when we look at when we keep the number of unfixed input dimensions fixed and just vary the epsilon ball that for the values these pixels can take, we still have the large weight below the diagonal and a lot of properties that we can prove that AlphaCrown cannot. That AlphaCrown cannot prove. Okay, I am quite fast today, which I did not expect. So it's already the summary slide. What have we seen? We introduced the first optimizable polynomial relaxations for neural networks with ReLU activation functions, and incorporated them into a linear back substitution procedure. And we were able to verify oftentimes more properties, and if we couldn't verify more properties, at least provide tighter bounds on many instances of our neural network verification problem. And with that, I thank you for your attention, and I'm open for questions.
Thank you. I was wondering one thing. So these sort of polynomial abstractions are very common in control theory. They're called Taylor models. So the innovation here is that you're doing the optimization, which is very interesting. But one of the problems they have with Taylor models is that computing these ranges LU that you have even here in the picture. So the range analysis, since you end up doing that over a polynomial, is as difficult as doing the range analysis of the original neural network. So how do you mitigate that? And doesn't that give you an unfair advantage in your comparison with AlphaCrown?
We mitigate it by using a very crude over-approximation for that. We basically just use interval arithmetic. So we first normalize all of the inputs to -1, 1 to get a centered form, and then we use interval arithmetic to calculate the bounds. And yeah, this should, in theory, or let's say in theory, there is always a configuration of monomial coefficients that gives us at least the same bounds as AlphaCrown, because of course every linear function can also be represented as a polynomial. And we have some opportunity for improvement because we are not restricted to these linear functions. So even though we use this crude interval over approximation, we can gain some improvements and achieve better bounds in many cases.
Any other questions? Do you have a bound on the degree of the polynomial, or it can go forever?
So in the implementation, we just looked at quadratic polynomials. But the formalism, it actually also works for polynomials of any degree. So basically what gets more expensive is, of course, you have more monomial coefficients, and you might need to use more expensive solvers to solve this univariate polynomial optimization problem.
we can thank you, the speaker, Philip. Thank you. Okay, so last talk. Yes, the NEAT paper. Exactly. Okay, so our last talk of the day is from Avaljot Singh from University of Illinois. The title is Constraint Flow, a DSL for specification and verification of neural network analysis.
Hi, good evening, everyone. Hello. Okay. Good evening, everyone. So I'm Aval, presenting Constraint Flow, which is a DSL for specifying and verifying neural network analysis. So we've seen in the past that AI is, although used quite a lot these days, but it is unreliable. There have been car crashes with autonomous driving vehicles, as highlighted by Katerina and other speakers. Self-driving cars and the automated systems for aircraft collision avoidance, they are not very good. They're not accurate. And that is far, even the smaller models are embarrassingly non-robust to small perturbations in the inputs. So in order to deploy these models to safety critical areas, for example, healthcare or autonomous driving, we need better metrics than just accuracy or precision or recall. And this is because even if some input is classified correctly, small perturbations to the input can lead to misclassifications. And think about these misclassifications in terms of healthcare, for example. It can lead to drastic results then. And this is where formal certification comes to the rescue. Let's assume we have a neural network classifier, and there are only two classes, A and B. And assume that this red line is the ground truth decision boundary, which we know. And this blue dot is some input point, which is correctly classified as class A. But what we want is that all the points in the vicinity of this input data point should also be classified correctly. And this is what is called the local robustness property and has been explored by many people. You can also define other properties, for example, global robustness or monotonicity, some properties over neural networks, but the basic idea remains the same. Let's look at some techniques that have been explored in the past to solve this problem. The first one is testing, which is very scalable. You just sample points from the input set, and you try to infer the outputs on those, and you try to check whether the property holds on them or not. Now, this is scalable, but this is unsound because you are not really certifying it. You're sampling the points. On the other end, we have you can encode the neural networks as in solvers, for example, SMT solvers or MILP solvers. Now, these are sound, and these are complete in most cases where you have piecewise linear activations, and there's nonlinearity, basically, or you can handle them in some way. But these are not scalable. They don't go beyond, let's say they will work for Akasu networks, or they will work for networks which are trained for MNIST images, but they won't go for CFAR10 or ResNets, and so on. Then in the middle, we have abstract interpretation-based CNN certifiers. There is a diverse range of them. They are sound. They are usually not complete, but that is not even required in most of the cases. We just need to certify the property. As long as that is done, we don't really need completeness. And the scalability, well, you can change the abstract domains, you can change the abstract transformers, and you can vary their scalability as per the use case. So these really offer you a wide range of DNN certifiers that you can use as per your application. And that is why this is the main target of our work. Let's look a little bit at how these abstract interpretation-based certifiers work, although I'm sure this audience has a good experience with these. But let's still look at it a bit more closely. So let's say this represents the set of images that you want to certify on. This is potentially an infinite set. but it is usually difficult to work with this set explicitly. So we usually over-approximate it. Let's assume that this blue region is the over-approximation, and this white region is the actual set phi. And this is usually done using some abstraction function. You use some abstract domain. Now, you define the abstract transformers or the transfer functions for each DNN operation, for example, the fully connected layer or the ReLU layer. And you keep propagating this blue set. We never propagate the white set because that is usually hard. But what is important is that the blue region is always an over-approximation of the white region. That is what we refer to as the over-approximation-based soundness. As long as that holds, the abstract interpretation is sound. But there are problems with the current development of abstract interpretation-based DNN certifiers. Now, the fundamental reason why that problem is that abstract interpretation is an art that not everybody can excel in. There is a set of people who excel in abstract interpretation, the maths behind it. But there's a different set of people who can work with neural networks, because neural networks don't work at the abstraction of a neuron or don't work at the abstraction of vertices in a DAG. They work at the abstraction of the whole layer, which are essentially tensors. And there are no transfer functions when you implement them. They are matrix multiplications. So you reduce all your transfer functions into matrix multiplications and then propagate them. So there is a semantic gap between the mathematical development and the implementation. So what are the kind of problems with the current development? So the neural networks are usually implemented as large arrays of layers, and each layer is itself an array. Either it's an array or it's pointer arithmetic. And these are very easy sources for unsoundness. Second, the implementations, if done by a math person versus as if done by a neural network person, they usually don't scale with the increasing size of the network. You really need optimizations. You really need tensor operations. So that is another problem. Third, sometimes when you design the transfer functions or the abstract transformers, they have mathematical unsoundness in them. They are just not sound. They just don't obey the over-approximation property. And fourth, as we have seen today, new DNN certifiers have already been proposed. One was the reduced product, which Katerina suggested, and one was the I forgot the name, the poly domain, which was suggested just in the previous talk. So if a new DNN certifier comes up, you have to implement it from scratch, and it takes you thousands of lines of general purpose programming to write those, and they are very easy sources of unsoundness. So what we propose is a new DSL, a new framework, which is called constraint flow, where the users first specify a very high-level mathematical description of the DNN certifier, abstract interpretation-based DNN certifier. The second step is we take the DNN certifier and we verify whether it adheres to the over-approximation-based soundness or not. Now pause here for a moment and think that the user is specifying a DNN certifier where the input is a DNN. But we are not verifying that. We are verifying whether the certifier is sound or not. So it's a meta-verification problem where you are verifying the verifier. Why is this important? Again, because every day new DNN certifiers come up, new DNN operations come up, so new DNN certifiers have to be developed for them. So we need one automated way to verify whether they obey the soundness property or not. And the third, we hope to build a compiler which can take that specification and then compile it down to the actual tensor operations, which are basically matrix multiplications. This is future work. The focus of today's talk is the specification and the verification of DNN certifiers. Now, several examples of DNN certifiers have been discussed today. These include the simple interval bound propagation, dpoly or crown, it's also called. They are essentially the same, but they were developed by different people. There is Vegas, and there is DeepZ. Let's look at some of them. We've already looked at them today, but now let's look at them with the perspective of what we need to specify them, the high-level mathematical specification. We really don't care about the precision. We really care about how to specify them succinctly and how to verify them. Let's look at IBP first. Consider a very simple neural network where you have two inputs, two outputs. It's given that the inputs lie in the range -1 to 1, they're normalized. And we want to certify some property over the output. For example, x11 is always greater than x12. Now this is the IBP certifier, which associates two things with each neuron. One is the lower bound, one is the upper bound. Let's call them L and U, small l, small u. And they're initialized with trivial bounds, which is -∞ and infinity. In the first step, you update the first layer, which is just which you just get from the input. It's just -1 to 1. And you keep doing the interval arithmetic. You keep going layer by layer. This is essentially a forward analysis. You keep going forward until you reach the last layer. And if you can certify the property, good. If you can't certify the property, either it doesn't hold, or you need to be more precise and you need to go to better abstract domains. But the main takeaway from that example is that IBP associates two things with each neuron. One is the lower bound, one is the upper bound. And it is a forward analysis. Right? Let's look at a more complicated example, which is the D-poly. But let's look at why do we even need D-poly? What's the problem with interval propagation? Let's say you have very simple neural network. You have x1 and x2, and the linear combination is x3 with 1 and -1 as the weights. And you know both of them lie between -1 to 1. Now the question is, what can you say about x3? It is simple interval arithmetic. We can easily say that it lies between -2 to 2. But what if you knew that the input to x1 and x2 was x0 with a weight of 1? Interval arithmetic will still give you the same answer, which is -2 to 2. But can you do better? If instead of storing -1 to 1, naively storing the concrete bounds, if you stored the polyhedral expressions, which is x0 here, you would have gotten that x1 minus x2 is essentially 0. Now both of them are sound, but one is more precise than the other. Now these are the polyhedral bounds which we will use, and we'll look at how D-poly exactly uses these polyhedral bounds to get better results. Again, we have the same example, same neural network, 2 inputs, 2 outputs. The inputs lie in the range -1 to 1, and we want to certify whether x11 is greater than x12. Now this time, instead of just storing the lower and upper concrete bounds, we also store capital L and capital U, which are the polyhedral bounds for each neuron. Again, everything is initialized with trivial bounds, which is -∞ and +∞. Again, we go step by step. The first layer just gets its bound from the input, which is just -1 and 1. So far, it's the same as IBP. Then, as you go to the second layer, since it's an affine layer, you can clearly see that x3, focus on x3. So x3 is just a linear combination of x1 and x2. So it's equal to x1 plus x2. So both the lower bound and the upper bound are essentially x1 plus x2. So this looks easy for a linear, for an affine layer, but it gets complicated as you introduce activations. For example, ReLU, I'm sure these things have been discussed in previous talks. So we'll skip them. But we want to look at how storing these polyhedral bounds lets you make the concrete bounds more precise. That's what we want to see, how D-poly uses it. So let's say we went to the last layer. I'm showing just some arbitrary layer, and we want to compute these bounds, given that you have the polyhedral bounds now. Let's focus on the upper bound, upper concrete bound of this neuron. So this is U11, which was the upper polyhedral bound, which we computed. Now, since it's a forward analysis, you already have the bound for x9 and x10. And I've worked out the example, and let's assume these are the upper and lower polyhedral bound for x9 and x10. We will replace both x9 and x10 individually with their own upper bounds or lower bounds, depending on the sign of their coefficient. In this case, both are positive, both are 1, so just replace them with their upper bounds, and we get new bounds in last to last layer. So x11 layer, then you had x9 and x10, and then you had x7 and x8. So in this layer, we get the bounds. Once again, we replace them with their respective upper bounds. And notice now, when you replace x7, you get x5 plus x6. But when you replace x8, you get x5 minus x6. So here's a chance that you can cancel the coefficients of x6. Right? One is positive and one is negative. Had it been IBP, you couldn't do anything. You just have to do the naive interval arithmetic. So it would be very imprecise. But here you can just cancel them out, and you will be more precise in IBP. This is what you get. And you keep going back layer by layer in the hope that you will get more opportunities to cancel out the terms so that you can be more precise. Let's say you keep doing this and you just go back to the input layer, which is x1 plus 0.5 x2 plus some constant. Now, at this point, x1 and x2 are really independent because they're given to be between the range -1 to 1. You can't do anything, right? So now you can replace them with their respective concrete bounds to get an upper bound of 5.5. Remember, in IBP, it was 7, and now we are more precise. For this particular talk, it doesn't really matter whether you can certify the property or not. My target is to show you that different certifiers do very different things, both in terms of abstract domain, in terms of abstract transformer, and how the constraints are flowing through the network. There are 3 things to it. So, by the way, this step is called the back substitution, where for each layer you want to compute the bounds, you traverse the whole neural network backwards at each step. So again, the main takeaway from that slide is that dpoly associates 4 things with each neuron: small l, small u, capital L, and capital U. 2 concrete bounds and 2 polyhedral bounds. Again, it's a forward analysis, but at each step of the forward analysis, it is doing a whole backward traversal throughout the DNN. Right? There's a third DNN certifier, which is called Vegas. Again, similar to dpoly, it stores all the 4 things, which are upper and lower polyhedral and concrete bounds. It again does backward traversal similar to dpoly, exactly same. But once it is done with the forward analysis, it does a phase of backward analysis. So forward and then backward. So it's that way more precise than dpoly. Then we have DeepZ, again I think was presented by Katerina, where instead of storing the upper and lower bounds, you store a zonotope expression, which are essentially expressions which are not in the neural network. They are noise variables, basically. Let's not go into the detail, but it is some other abstract domain and abstract transformers. But essentially, it is again a forward analysis. Now, again, what are the key components of specification of this DNN certifier? The first one is the abstract domain. But we focus on the abstract domains where you associate some fields with each neuron in the neural network. Right? For example, in IBP, it was just the small l, small u. In all the other, it was small l, small u, capital L, capital U. And what is the abstract element, essentially? The tuple of, so by the way, these 4 things we call as the abstract shape of each neuron. And so what is the abstract element? The tuple of abstract shapes of all the neurons in the DNN. That is basically the abstract element. But it can be succinctly specified by specifying the abstract shape of only one neuron. That suffices, because everything is the same. The second step is to specify the abstract transformers. Now, what does this mean in terms of specification? For each DNN operation, which can be affine, ReLU, maxpool, sigmoid, anything, for each of them, you need to specify the computations for each element of the abstract shape. For small l, small u, capital L, capital U, you need to specify how to update them. That is basically the abstract transformer. Now, if you see this abstract domain, when we associated this abstract shape, this essentially associates constraints with the possible values of the neuron. Right? So the abstract shape can also be thought of as the constraints on the neuron. And so the last step is to specify how are these constraints flowing through the neural network, whether it's a forward analysis, or it's a backward analysis, or it's a combination of both, or you can do any kind of interleaving between them. So this control flow, hence the name constraint flow. You are defining the constraints, and you are defining how are these constraints flowing through the neural network, instead of just flowing some data point. Now, let's look at how would you specify dpoly in constraint flow. So the first step was to specify the abstract shape, and which will induce an abstract domain. So the abstract shape was essentially 4 things: small l, small u, capital L, capital U. Small l and small u were just floats. Let's not distinguish between floats and reals for now. They are just all the same things. Capital L, capital U were polyhedral expressions. Now, polyhedral expressions are very extensively used in terms of in this application, DNN certifier. So better to introduce them as data types in the language. And most of the arithmetic on polyhedral expressions can be automated, for example. For example, the plus, you don't need to write the polyhedral expression as an array of coefficients and then add them. You can just overload the plus operator and define the semantics. Then you also specify, along with the abstract shape, what is the over-approximation based soundness that these fields associate with the neuron. So what are the, so by the way, this abstract shape is defined for a neuron which we call as current, CURR. And it is just a syntactic holder. The same abstract shape is associated for all the neurons in the neural network. And what is the property that is associated? that L is less than current, U is greater than current, capital L is less than current, capital U is greater than current. This is the soundness property that we also want to verify, whether all the abstract transformers, they adhere to this property or not. Next, before we can define the abstract transformers, we want to define some user-defined functions. So let's look at an example. While we were doing back substitution, if you remember, we were replacing each neuron with either its lower bound or upper bound, depending on the coefficient. Upper and lower polyhedral bounds. So we call these functions as replace lower and replace upper, where you have a neuron and its coefficient. Depending on the sign of coefficient, you either replace it with its own lower bound, polyhedral bound, or polyhedral upper bound. And similarly, you have a replace upper function. Similarly, when you reached the input layer, you didn't replace them with their polyhedral bounds. Now you replace them with their concrete bounds. So that is what we call as the concretized lower and concretized upper. Again, the same thing, you have a neuron, its coefficient. Depending on the sign of its coefficient, you either replace with the lower bound or the upper bound. But this time it is a concrete lower or upper bound. And then using these, you can define the back substitution function, basically for the lower bound. And similarly, you can also define it for the upper bound. Now, this back substitution was essentially a graph traversal, a whole DNN traversal. The DNN can be thought of as a graph, a DAG, right? So it was a whole backward traversal. Now, how do you specify this succinctly? First, you specify what is the direction of traversal, which is backward in this case. Then you need, so this traversal can be thought of as having an active vertex set. And in that active vertex set, you associate the priority with the vertices. The vertex with the highest priority is to be traversed next. So this is a way of specifying the graph traversals, which is basically which direction you go, what is the priority of applying, of doing the traversal. Then depoly can be made more efficient by stopping the back substitution at some intermediate layer. You don't necessarily have to go to the very input layer to be to get the concrete bounds. You can stop the analysis somewhere in between. So you can define some custom stopping function. Here false just means don't stop anywhere, just go back to the input layer. But you could have some custom stopping function. That is the third argument. And the fourth argument is while you are traversing, what is the replacement function? What do you do with each neuron? What do you mean by the traversal? And that is basically the replace lower function. So once you execute this traverse, you will get a polyhedral expression which is in terms of the input layer neurons. And once you do that, you want to concretize all of them. And that is how you do it using the map construct. It will apply this function to each of the constituent neurons of the polyhedral expression. Sorry. And then this, we'll come back to it later, but this is, so essentially traverse is a graph traversal, which is a loop, while loop. Now, although we don't explicitly allow loops in this specification, but this is a loop, right? You don't know how many layers you will go back. You don't know what is the architecture of the DNN. You still want to verify its correctness, so we basically rely on invariants. Now, currently, these invariants are just user specified. The user gives the invariants, and we will verify them. Similarly, you can, I mean, this was the traverse and map. Again, these are defined on the data types, which is the polyhedral expression. And you can similarly define the back substitution upper. Now, once you're equipped with these functions, the user-defined functions, you can define the abstract transformer, which we call as depoly. And you have to define it for each DNN operation. You have to define it for affine, for ReLU, for maxpool, for sigmoid, everything that is there in your neural network. And for each of these operations, you need to define 4 things. This is for small l, for small u, for capital L, and for capital U. So 4 things for each DNN operation. It really depends on what your abstract shape is. If it was IBP, you just need 2 things. If it is deep Z, you need 3 things. So it depends on what your abstract. For example, if it is the reduced product, you need as many things as it is a reduced product of, right? They are basically 5 things, I think. Finally, you need to define the flow. How are the constraints flowing? Again, it's a forward analysis, so the direction is forward. You need to give the priority function. False again means just don't stop anywhere, go to the output layer because your property is defined on the output layer. And what transformer to apply as you're doing the forward analysis is depoly, which you just defined here. So this is how within less than 15 lines you can specify the depoly depoly DNN certifier. And in its implementation, it's actually thousands of lines of code. But this is what you actually need to mathematically define it. why are those thousands of lines? Because they are coupled with optimizations and implementation details and whatnot, which is also harder to verify, by the way. Now let's look at dpoly's ReLU specification a bit more closely, as we've already done. So it's usually specified in 3 cases, depending on, so the x-axis is the previous neuron, this prev construct is the input to the ReLU, and cur is the current neuron, which is the output of the ReLU. Now, depending on the lower and upper bound of previous, the ReLU is specified in 3 cases. One, when both are positive, the lower and upper. One, when both are negative. And the third case, which is the more tricky one, where they are in the opposite direction. So here, you can define the upper and lower polyhedral bounds as these lines. And this is how you would specify this in constraint flow. You can use these ternary operators, question mark, and followed by colons, to specify the 3 cases. Again, just summarizing, what is our soundness property? It is already defined by dpoly. L is less than n, U is greater than n, capital L is less than n, capital U is greater than n. Now, what happens when you execute this? You don't have one previous or one current. You have a layer of previous neurons. There is essentially one layer of ReLU neurons, which have as many previous as the number of neurons there, right? And you have the current neurons. They already have some abstract shape associated with them, which are maybe just trivially initialized with -infinity and infinity. Or maybe they have some other bounds. It's a, let's say, forward, backward, and then again forward. So they will already have some bounds. And when you apply the specified transformer, this will essentially update the shapes of all the current neurons. This is what will happen when you actually execute the specification. But this is not true for verification. What happens when you verify it? You want to verify the specification for all possible previous and all possible values of current neurons. It is not fixed. It is, so when you are verifying a DNN certifier, the actual DNN is an input. You want to verify the soundness of the DNN certifiers for all DNNs. So there is a universal quantification over the neural networks. So that's what makes the problem a little bit more hard. So again, if you have arbitrary previous, arbitrary current, they already have some shapes associated with them. And when you apply, these shapes are updated using these primes. Now, when you are verifying that these still obey the over-approximation-based soundness, what are your assumptions? The assumptions are that the initial values of previous already satisfy this, because it is basically you are trying to verify the induction step now. You are doing it forward analysis. So previous already satisfies the property. Current also initially satisfies the property. You also want to say that current is equal to the ReLU of previous. One more important thing, when you update the shape of current, which is basically these things, the current is still ReLU of previous. That doesn't change. The relationship between current and previous is still intact. Only the abstract shape changes. And now you want to verify with these updated shape, is the over-approximation property still, does it still hold? So basically this is your SMT query, final query. We offload it to some SMT solver. Now, this looks simple, but there are several challenges when it comes to verification. First, the example that I showed you was on fully connected neural networks. I mean, all the examples that we've discussed today were essentially on fully connected feed-forward neural networks. But the neural network architecture can be arbitrary. It can be any DAG, right? So you want to verify the correctness of the certifier for all possible DNN architectures. Second important challenge comes from the DNN certifier. Now we saw, for example, dpoly, this associates polyhedral bounds with a neuron. N1 is greater than, let's say, N1 plus N2. Now these, let's say this N was from layer F. It is not necessary that N1 and N2 are from the layer E. They can be from anywhere in the neural network. So there is an additional structure imposed, which is beyond the neural network architecture, which is not, so first thing, DNN architecture is not known when you are verifying. You have to do it for all DNN architectures. Second, even if the DNN architecture is known, there is an additional structure imposed by the DNN certifier, which is not known unless you execute the certifier. So this is a multi-step challenge. This is still an ongoing work. So I'm not going into the details of how we do it, but we've had some early evaluation. We want to evaluate on 2 parts. What is how good your specification is and how good your verification is. In terms of specification, can you specify the existing and new certifiers? And in terms of verification, how much time do you take to verify them? So in terms of specification, we can specify a lot of the DNN certifiers in less than 40 lines of constraint flow code. And we can even come up with a new certifier, which was maxpool. I'll suggest you to read the paper. I don't have the time to discuss it. But it's more precise than depoly, and essentially the particular transformer has the same runtime. I can't comment on the runtime of the whole DNN certifier, but that transformer is same runtime as depoly. And we were able to verify this new transformer. By the way, we can also specify poly Z or the reduced product or the one which was just introduced in the previous talk. In terms of verification, we can verify the ReLU, minimum of max pool, those all kind of things. And the primitive operations can be verified within a second, and these composite operations can be verified within few minutes. And these are DNNs with millions of parameters for each layer, and the number of layers can be arbitrary. Just talking about the future directions. Again, the compiler needs to compile it down to tensor operations. It is not the per neuron specification which works. It is the tensor operation which works. So we need to reduce these these abstract transformers to tensor operations so that they can actually be implemented on GPUs. So that is one future direction. Second, we need to specify the relational specifications. For example, you want to compare two neural networks, or you're given a neural network and you want to say what happens to two inputs, for example, hyperproperties, or for example, to abstract shapes that are defined on multiple neurons at the same time. Third, how do you handle nonlinear activation functions like sigmoid? And fourth, this gives you a grammar and a verification procedure. So you can design a program synthesis approach where you can automatically come up with new certifiers because you already have a grammar, and you have to verify whether each candidate is that sound or not. So you can essentially design some program synthesis on top of constraint flow. So that's the talk. And
okay, we have a time for a couple of questions. Rick?
Have you a way to compare specification, like proving that one will always give a better result, more precise result than another one?
So far we have not looked at it, but the property that you initially specified with the abstract shape was a soundness property here. It doesn't really matter what the property is. You can specify some precision-based property, whether you can specify that this is the precision of IBP, and this is the new precision that we define for depoly. Is it always better than that? So we don't really care what the property is. Once we have a way to verify it, it can be any property. So we haven't explored it currently, but we can extend it to the precision-based properties.
Also, there are notions like reduced products. Can you say, I take two specifications, I combine them in some way or another?
Yes, we have already tried to specify the reduced product of deep Z and depoly, and we can verify, yes.
So I'm still confused about why the DNN architecture matters when you're trying to verify, because it's just sort of the usual way you do it, any abstract interpreter, is you have your program, you reduce it to some IR, and you reinterpret each operation in the IR, substitute with this abstract form, which is sort of what you're doing in the context of DNNs. But you don't say, oh, for all programs is my abstract operation sound. You usually do it like locally, right?
But this is a meta verification problem, right? You want to verify the soundness of the certifier.
Yeah, I'm talking about soundness of the certifier.
So
like when you have a sound abstract transformer, you just talk about the abstract transformer being sound, irrespective of what the rest of the program around it is, right?
So DNN is essentially an input to the certifier, right? It is not a part of the certifier. So it's not a part of the program that you want to verify. It's an input to the program that you want to verify. And the second thing is, when you execute the certifier, it introduces arbitrary connections. For example, in the case of polyhedral bounds, when you say n is greater than or equal to n1 plus n2, these n1 and n2 can be from anywhere in the neural network, right? You don't know whether they are from just from the previous layer where you have already verified the property, or they are from the forward layers where you have not yet verified the property. You don't know about that.
But if your abstract transformer is sound, it shouldn't matter.
That is what you have to verify.
No, but so that's all you have to verify, is what I'm saying. Why does the architecture matter?
All I'm saying is the architecture should not matter. It should be for all architectures. That's what I'm trying to say.
Am I?
So there's a universal quantification over the neural networks, right?
You're saying right as if that's very obvious to me. It's not. Like, why is
so you have a DNN certifier, which takes an input, a DNN, and operates on it. So DNN is an input to the DNN certifier. Now, when you want to verify the correctness or soundness of a certifier, you want to verify it for all possible inputs, right? When you want to verify that a factorial program is sound, you don't say that it is sound for x equal to 2. You say for all possible x's. So what is x here? X is the whole DNN.
When I write an abstract transformer for an addition in my C program.
Addition, it's easy because there are essentially two neurons.
But I just talk about that the addition is sound.
Yeah, you're right.
Given any abstract input, when I add them, multiply them, do anything more complicated, I get a sound output.
Yeah.
And I stop there.
Yeah.
And if this addition occurs anywhere in my program, that addition is sound.
Yeah.
And as long as each operation in my program has a sound abstract transformer, my abstract interpreter based on those sound abstract transformers is sound if you do the right thing.
Yes.
Right? Like the basic fixed point. And here there's no fixed point, you're just going.
Yes. Yes.
So
no, but that is also part of the specification.
You just go forward or backward, whatever.
Yes.
Right? The control flow is fine. So why does the architecture matter? Why can't I just do soundness per operation? And that implies that universal quantification over the architecture is true.
Well, in a way, it does imply. But what I'm trying to say is doing that is not very easy because for example, D-poly, it associates polyhedral bounds, right? It says N1 is greater than or equal to N1 plus N2. You don't know whether you have already verified it for N1 and N2 or not. You don't know what is the connection between N1 and N2, right? For example, let's say it says N is greater than N1 plus N2, but when you actually execute an N1 and N2 with the same neurons essentially, does this affect the soundness of your certifier?
I don't know what N1 and N2 means. So maybe we can take it offline.
Yeah, we can take it offline, yeah.
Okay. Another question.
So when you certify the certifiers, in the end, I suppose you get some proof obligations that you have to take care of.
Yes.
You hand them.
Yes.
Can
so
the SMT solvers?
Yes. So we essentially convert it into SMT queries, and then we offload it to, for example, Z3, and we verify whether that is.
And that doesn't pose any problems at all.
That does in several cases. So basically, this is a bounded verification. You will assume some bounds on the size of the layer, but it's only per layer. So those are realistic bounds, but at the end, it is bounded verification. It has to be a finite query.
Okay. I have maybe a little question. Maybe it could be interesting to extend the framework also to not only certify soundness, but maybe a kind of a partial completeness in this case.
Yes, definitely. I think that question was asked before also. So it doesn't really matter what the property is. Once you have a way to verify the soundness property, you can extend it to other properties. But you need one way to verify some property, and we start with soundness because that is really the most important one.
Okay. Last question because we are running out of time.
Okay, so this is also a question related to the SMT solver at the end of your analysis. So okay, you have a proof obligation and you give it to the SMT solvers. But SMT solvers are limited in the kind of property that they can prove automatically, in the kind of property that you can express. So have you found difficulties caused by that, or things that you would like to see be extended in SMT solvers?
Yes. So we can only handle properties that are piecewise linear. So basically, if the proof obligation fits into some SMT theory, we can work with it. Otherwise, we cannot currently. But the hope is that once this is done in the future, you can extend it to delta complete procedures, and you can have some way of approximating those queries in some way. So again, that verification will be sound, but that will itself not be complete then. But currently, we don't worry about those things because there are other problems at hand. But it can be extended to that.
Okay, let's thank the speaker again.